Good evening, everyone. Am I audible?
Yes, Mugda, you're audible.
Yeah. Good evening, everyone. A warm welcome to one and all for the day 3 of Atal FDP on millimeter wave technologies organized by Electronics and Telecommunication Department, BSET. This is Assistant Professor Mugda Zogadekar from Department of Electronics and Telecommunication. It is indeed privilege to introduce Dr. Biswajeet Mukharjee, expert of today's session. Dr. Biswajeet Mukherjee is an associate professor in the Department of Electronic Science at University of Delhi South Campus. With a career spanning over 2 decades, he has worked extensively in antenna, microwave engineering, electromagnetics, and related fields, guiding numerous PhD and MTech scholars. He has secured significant research funding exceeding 90 lakhs from various organizations such as Department of Science and Technology, Government of India, Madhya Pradesh Council of Science and Technology, and many more. Dr. Mukherjee has received many awards and accolades like IEEE APS MTTS Joint Chapter Gujarat Section Award for Innovation in Antenna Technology in 2023, recognition among the top 2% scientists of the world by Stanford University in 2021. He has been awarded for academic excellence, including the Hari Om Ashram Prerit Hari Vallabhdas Chunilal Shah Research Endowment Prize in 2017 and Young Faculty in Engineering Award by Venus International Foundation in 2017. His international recognitions include travel grants and fellowships from organizations like SERB, DST, and INSA, enabling his participation in global conferences. With 65 journal publications, 48 conference proceedings, 2 books, 3 book chapters, and multiple patents, Dr. Mukherjee is prolific contributor to his field. His dedication to research and innovation continues to inspire and advance the frontiers of electronic science. Dr. Biswajeet Mukherjee is a well rounded individual who excels his profession and strives to make positive impact to both his personal and professional spheres. We are having such a great personality among us for delivering the session on millimeter wave communication system, RF microwave antenna at front end for 5G. Sir, it is really a pleasure to have you for this session, and I formally welcome you and request you to take over. Over to you, sir.
Thank you so much, ma'am. It's a huge honor. I mean, the way the whole introduction has been read. Unfortunately, I don't know why the video is actually not working. I've been trying to work out on the. I've been just trying to work out that if the video could actually work. If you so permit, can I just for a moment just log out and then rejoin, and possibly that might just correct it if you just so permit me.
Yes, sir. Yes, sir.
Yeah,
Yeah,
sure,
yeah.
sir. No problem.
I'll just rejoin in a second, ma'am. I'll
Yes,
just
sir.
Yes,
rejoin.
sir.
I don't know why it is still not turning on the camera. It's quite unfortunate. Anyways, maybe I'll just continue, ma'am, because I don't know why this is not turning on the camera. There's some trouble which I'm facing still. Anyways, let's ma'am go to the lecture part. So let me first thank. I hope that's not a problem, just in case the camera is not turned on, ma'am.
Yeah, it is okay, sir. No problem.
Right. Right. So let me thank the organizers to have for this illustrious welcome that they have extended, and it's really an honor. Thank you so much to have invited me and to talk on millimeter wave communication system, which is RF microwave and the antenna front ends. And when I actually put it up, when I actually look up to this complete topic, which is dealing with the complete RF and microwave fraternity, I would always like to inform that there are a lot of pitfalls in this complete system. It's not that easy to come up with a complete system altogether as a solution. I'll try to cover up some portions of the RF and microwave systems which is eventually being used or to be deployed for the 5G communication systems. We will try to cover up most of them, right? With this, let me just start off with the complete the presentation only. All right. So, is the screen visible to everybody?
Yes, sir.
Yes, sir.
It's visible? Okay. I hope that it is also scrolling at the same time.
Visible, sir.
So now it's, I think, clear, right? So I've just put my small credentials that I'm what I am affiliated with. Currently I'm working as as associate professor at the Department of Electronic Science. As a brief background to what this department is, we came back, this department started off with a course on microwave electronics way back in 1976 as a program of the Ministry of Electronics and Information Technology. And it's almost like 4 decades old that the department as well as the program has been commencing the MTech program in microwave electronics. So you can say that Delhi University South Campus Department of Electronic Science is one of the pioneers of the field of RF and microwave technology, and its contributions have been quite extensive. And I always take this extreme pride to have been associated with this department over here. I completed my MTech also from here, and so I'm back to my alma mater altogether. And for 14 years, I was working with Triple ITDM Jabalpur, wherein most of the work actually has been done through various research projects of DST, MPCST, and the other sponsoring agencies. So whatever I'm trying to do is big thanks to all my sponsors who have sponsored all the external funded projects to me. So this complete presentation that I'll talk of is basically divided into three important segments. The first part is where we will only talk of predominantly the necessities of millimeter wave and what are the challenges in the 5G deployment, because 5G is still on a process of a rollout. We are looking up for the 6G roadmap, but then 5G is still on the pipeline, is still being coming up slowly with all the corrections and feedback which is being taken from the users, from the mobile, from all the mobile operators, from TRI, and from the source as well as the users. At every point, the feedback is being taken and then recorrected so that you could get an efficient application of this 5G network. So the first part will be dealing with mostly that. Second part, I'll be talking about what are the different antenna front ends which actually need to be dealt with. And I'll also talk about some of the antennas which we have worked at Triple ITDM Jabalpur as well as at Delhi University, my current affiliation where I'm now posted, where I'm now currently working. And the third part would be a very quick access to what all active components actually we need to look up to. Right. So if I just very quickly go ahead with what is the key motivation of working out, with 5G. So we need a lot of application scenarios. There are a lot of engineering requirements which we have in the fifth generation system. Some of them is that we want the data rates to be extremely high. We do not want that there should be a latency or there should be any sort of delay in any of the information which has to be processed. And so this one of the possible solution is massive MIMO. So one of the key technologies which we are actually looking up for rolling out 5G is massive MIMO, which is where a lot of focus on the electronic segment and the hardware section is already on. Because what we are referring to is the front end part of any communication. When you're referring to antenna, when you're referring to power dividers, couplers, or you're looking for the sources, even the amplifiers which are to be designed for the 5G section. So we are at the front end part. Back end would be the signal processing, right? So where we need to process all the signal, extract the information, do the demodulation schemes and whatever modulation schemes are needed, so on and so forth. So that is taken care of by signal processing and the communication group. There is one part on the amplifiers where there is a great contribution which also comes from the microelectronics group. But these part actually do not matter much to the RF and microwave people, because for us anything and everything is a high frequency carrier. So we already have this high frequency signal which has to be transmitted through the electronic component. So what is of our actually interest is the massive MIMO part, or the millimeter wave, where we are trying to either migrate, or the cell densification, which wherein obviously the cell sizes will eventually become extremely small. So when we look onto any of the wireless communication, one of the fields which is actually taken up, one of the figures which is taken up of Martin Cooper, who actually talked about spectral efficiency, and his statement was that the spectral efficiency, or the simultaneous voice and data connection, will be doubled every 30 months since the beginning of the wireless communication system. Now, this is something which is very, very in synchronization with the Moore's law that we have, many of us might have actually that we have studied in the case of solid state devices and microelectronics. So Moore's law also states that the number of components in the IC will actually increase exponentially. Same way, Martin Cooper's law of spectral efficiency said that the requirements of this simultaneous voice and data connection is going to double in every 30 months ever since the beginning of wireless communication. And it is actually so true. Most of us are teachers over here, born in the age of born in the era of either 1960s, 70s, 80s, 90s, so on and so forth. Even if it is, let's say, the children who are from early 2000 would actually connect to the fact, or they must have seen the evolution of wireless communication. So from very heavy handsets, we have actually come down to certain very small set of mobile phones, which today are capable of doing both. Number one, the internet connectivity. Second, your mobile phone connectivity. So both of them are actually on, and the complete genesis of the systems from 2G to 3G to 4G to the next set of generations which are supposed to come up, all this stands as almost a miraculous feat of achievement, yet in a very, very, very small time frame. If you talk about a very small time frame, because 2G came back in around 1990s, and in fact in India it came somewhere around 1997, 98. And I'm sure if somebody really had a mobile phone, or they must have connected also at that point of time in 97, 98, the call rates were extremely high. If the best of my memory supports me, it was almost like 16 rupees a minute for an outgoing call, and 8 rupees a minute for an incoming call over the mobile phone. That was the call rate that we had. I'm not even referring to something called as pulse rate, which people had generally for STD and ISD connections. So from there, if you compare today, 2024, somewhere from 1998 to 2024, it's almost like 30 years. The call rates, the facilities which we are now getting is extremely, extremely vivid, and very, very, it's very prudent. It takes care of almost everything. So each generation, so 2G, 3G, 4G, I think we can all read, but each generation is adding to, number one, the higher data rates. Second, new spectral bands, because we cannot operate. It's very obvious that you cannot have a very wide bandwidth on a lower set of frequency. So obviously we have to go to the higher frequency. So when you go to the higher frequency, then you get a wider band. So we are generating new frequency bands, and it is bringing up certain new set of technologies which we will actually discuss also. This is again a comparison of the future predictions. Now again, if you go back, when this course on it is quite interesting for me to quote at this point that I've studied the course of wireless communication 4 times. The first was in the seventh semester, the first was in the sixth semester, when only the basics were actually taught. The second time when we studied a detailed course on wireless communication was in the eighth semester specialization, where we were taught, what was 2G and what 3G would actually look like. When we came to MTech, When I came to actually MTech, so again the course structure was different. We talked about 3GPP and how IP traffic is to be put up on that, and how the devices are to be connected. And when I went to PhD, I had the fortune of studying from the current scientific advisor to the current secretary to Department of Science and Technology, Professor Abhay Karandikar. So he taught us the complete traffic theory, which has to be mapped for such a high amount of traffic which will be deployed. So the what the genesis, if you now look up from all these these topics being correlated, is the number of devices that we are connecting. We never imagined that when somewhere the mobile communication or any of these communicate wireless communication ever came up, that we will have multiple set of devices connected. We never had that in mind also. Why? Because there was one mobile phone which you could actually carry. Go one step behind, having a cordless phone was a very big feat of a kind of a chivalry, a kind of a chauvinism for somebody, that we have that we can afford a cordless phone in our house which could give us freedom from wires. So mobile communication was a very big leisure. So we never talked about number of devices to be connected to it. Then came the word modem, wherein very small amount of traffic over the internet was actually passed through the two-wire transmission line of the telephone cables, and then modem used to give us a connectivity. We are dialing the number, and then eventually the mobile, the complete internet could be actually connected to it. However, if you look today, we are talking about multiple devices to be connected over the wireless communication. So basically, my mobile phone that I'm actually using is not just one single device, but it is capable of controlling almost every gadget that we come across. There is a Bluetooth speaker we can connect to. We are connecting it to our respective vehicles which we are driving. We are connecting it to our smartwatch. We are connecting it to almost name anything that we feel like. We are into the kind of a smart world. So the number of devices which are to be connected is exponentially increasing. At the same point of time, when you look onto the global traffic, obviously that will also become exponentially high. That will also increase. So that the same thing has been quantified, that the total growth of the traffic has almost become 7x times. And by 2021, we already had 12 billion interconnected devices. This is one of the problems which was actually posted somewhere in 2021, when we were looking for the roadmap for 5G rollout and subsequently the 6G which has to come up. So what are the different things which we expect from 5G use cases? One of them being given over here for Ericsson, what they have actually thought of. Either it can be a broadband experience. That's obviously, when you are looking for broadband experience at almost every place. So one of the examples where broadband experience was rolled out was the Winter Olympics, February of 2018 in Korea, wherein 20 Gbps of data was actually given or awarded only for the Winter Olympics hosting. We needed a lot of things, tracking also, because when you are talking about when you are talking about Winter Olympics, which are extremely crucial, let's say you're talking about skiing, you're talking about skating, you're talking about different set of events which are taking place over the ice, tracking every individual is extremely important. So you want GPS locations, you want their dynamic locations to be updated, so that in case there is some emergency which is taking place, the help should reach immediately. So we wanted a very, very high amount of precision. How do you get that precision? When you have a very high bandwidth. So that is something which was rolled out way back in 2020. Then we also want autonomous vehicles, which is also the driverless vehicles at the same point of time. So most of the things were eventually taken care of when you are actually trying to create a roadmap for the 5G altogether. So what's a few of those examples are like Volvo, Uber, who are actually using these autonomous or the driverless cars, which is already rolled out in US. And I think one experiment successfully has been conducted even in Indore, which was there in the newspapers a few days back. Internet, media everywhere, obviously. If you actually ask somebody that what keeps you busy, the best thing is your mobile phone, because you can open your YouTube channel, you can check out your YouTube videos, or you can just get an access to any of the YouTube videos that you want to see at any dynamic point of time. And most of the children are also, that's why they're pretty occupied watching reels, watching their, their favorite cartoon shows all on the mobile phone. Gone are the days when, people used to connect it to the TV and then they used to watch. I think everybody is now into their respective mobile phones. And the last part is Internet of Things, that is expected in 5G, wherein we will connect all these devices and components in order to get dynamic data. For example, for agriculture, soil monitors in the farm. This is one of the critical examples where people actually want it. GPS location. So when there was this hall which was created in IIT Delhi, and Mark Zuckerberg was invited in the open hall of IIT Delhi. He was asked that what do you expect with Facebook next? So he said, obviously with 5G and 6G, I want the dynamic location of every individual to be mapped so that we can have minimum tragedies. We'll be able to get the precise location, movement, security purpose also. If we actually look up, it will give us the maximum precision data. And so that is one of the things which we are looking for 5G and 5G onwards. So what are the different engineering requirements when we are looking for such a holistic and kind of a vision roadmap? The typical data rates we are talking about is 1000 times increase from 4G to 5G. The cell edge user rate will actually increase by 100x time. Reduce cost per bit. Obviously, I would like that what we would actually expect is that the cost of operation should be as minimum as possible. If the cost of the operation is extremely high, then obviously we will not be able to afford it, and so we will not go ahead with it. And latency time has to be much less. It has to be lower than typically 1 millisecond or maybe even less. So we want that the web pages should be uploaded or it should be loaded immediately. So these are some of the requirements of 5G which we want to meet. And so you cannot have the conventional cellular network which we used to have in the 2G and 3G scenario, with one base station being posted at the center and it was giving you a kind of a coverage. The cells actually have to now decrease. So if the cells decrease, that means more number of cells are to be added up, and so that means cells densification. We want that there will now become more and more number of cells, and the cluster size will actually decrease. So eventually we want more number of cells in one particular cluster. And at the same point, that's, by the way, when I'm saying this, I'm referring to the fact that one geographical area remaining the same, geographical area not changing, the cell sizes are now decreasing. So the density of the cells in that geographical area drastically increases. So the question is, how do you get this 1000x in data rates? We'll get back to one of the conventional definition of throughput, which is cell density multiplied by the available bandwidth multiplied by the spectral efficiency. And I've also given all the units. If we increase the cell density, then also we can improve the throughput. If we have a higher spectrum, when we migrate towards the higher set of frequency, obviously bandwidth increases, so that will increase throughput. And third is spectral efficiency. In order to improve the spectral efficiency, we can go for MIMO, but that is multiple input and multiple output antennas. That is what we are trying to look up for. So all these three multiplied together will actually give us a very, very high throughput and very improved throughput. So one of the examples wherein we are looking for now higher set of density is that instead of having the conventional 7-cell cluster, so we have talked about the cluster system by using a simple conventional formula of I square plus j square plus ij when we teach it to our students also. The same thing continuing, but now we want more number of cells. So the density is now increasing. That is what we are actually looking for. And the trouble with these extreme densification is, number one, deployment cost. More the number of cells means more amount of hardware. I need those many number of antennas also to be deployed. So that is rent, installation, maintenance, everything put up. There is a strong chance of interference, especially for LOS and the path loss being 2. In fact, when you go for a very, very high densification, then the path loss will not even remain 2. The path loss exponent will also change. How do you accommodate that? That becomes a trouble. The SINR, that has to be significantly to be taken care of. In fact, this SINR was never a problem when we were actually referring to CDMA. Quite interestingly, when we were teaching CDMA to our students, we always said that although everybody is operating on the same bandwidth, yet we are getting a full communication established. And why is that happening? Because everybody has a different code. So let's say I am communicating in Bengali with my Bengali counterpart, and at the same point of time, on the same frequency, somebody is communicating in Marathi, somebody is communicating in Telugu. So that is how we established that the code division multiple access was going on the same frequency, despite the fact that the frequency was same. But here we will now have problem. We will also have a trouble of the frequency allotment, because even if you go for higher set of the bandwidth and operating frequency, the number of channels which are to be deployed will again remain a bone of contention altogether. So complete of, if we actually look up, the open source problem remains interference suppression techniques in this ultra dense network with appropriate propagation model, because the propagation model will not remain the conventional two-ray model anymore. That will also change. However, the two-ray model part is more of allied into the communication section. What is of my interest is that if the ultra dense network remains, the spectral efficiency part can be taken care of by MIMO, by arrays, and by beamforming techniques if we are going for millimeter wave, because we have to look up for this high frequency challenges. So the spectrum allocation, when people started looking up for, we anything which was in the sub 6 gigahertz was already occupied. You pick up from 1 gigahertz, in fact, just trace it back to megahertz onwards, wherein we start with HF, VHF, UHF applications, go on up to the 2G networks at 1 gigahertz. In between, you have got tetraband also, wherein we are doing a lot of classified applications. From 1 gigahertz to 2 gigahertz to 3 gigahertz, we have got immense number of other applications, right from microwave ovens, we have got Bluetooth, we have got Wi-Fi, WiMAX, all leading up to the 6 gigahertz. So the spectrum of sub 6 gigahertz, although it is more preferable, it is extremely congested, and anything above the 6 gigahertz remains quite idle, wherein we are referring to most of this millimeter wave range, right, up to 300 gigahertz or maybe even beyond. Most of these bands are still not occupied. The challenge is electronics. How do you actually devise all the basic components? That becomes a very big challenge over here. So we have to go up in the frequency. The challenges with millimeter wave communication is that, number one, there will be a very high propagation loss. When we are looking for propagation loss, it is proportional now to fc square, so we will have a trouble with the propagation phenomena altogether. Atmospheric rains, atmospheric effects, they become extremely prudent. So if you if I'm sure everybody has a DTH at home, so the moment the outside atmosphere becomes cloudy, all of us get a message that which is flashed on the screen of our televisions, or whether LCD, LED, whatever, or OLED or QLED, whatever we are using, that there is either there is a possibility of rain, or there is a very high cloud coverage, which is why we are unable to get any signal. So we have got these water absorption peaks. So the complete millimeter wave range is extremely prone to it, sensitive to extreme blockages also, because the diffraction becomes extremely sensitive. So of course, any blockage would or by any object, that is also another set of a problem. And it can only be used for small cells. So it's very, very obvious when you go higher in the frequency band, the light becomes the electromagnetic wave starts traveling in straight line, so it becomes a line of sight. At the same point of time, we also need beam steering technology, which can be done only with the large the large antennas will be able to do it. So the trouble is, how do we come down to, if we go ahead with these set of problems and challenges at 30 to 300 gigahertz, or maybe around 20 gigahertz onwards, the only biggest problem that we now face is, how do you get the electronics deployed? That's a very big challenge. So most of the things were actually deployed on the when we look on to the complete 5G spectral part, the most of the things were actually brought down to 6 gigahertz level. So this is one of the things wherein the IEEE transaction came back in 2017, wherein most of the requirements of 5G were actually being put up, right from data rates which were expected to go up to 1 Gbps. We talked about the connection density, we talked about the latency also. So this was actually being put up as a strong proposal, and it was published somewhere in transactions in 2017. In the volume 65 number 12, you can check out from the reference also, wherein the roadmap for 5G services was first being laid. So what are the enabling technologies? The keywords or the buzzwords were ultra dense networking, We needed novel multiple access techniques, so the conventional multiple access techniques won't work. We wanted all spectrum access, massive MIMO, which has to be deployed. So it's not just two element, four element, it is multiple set of now elements to be connected to the same set of communication strategy. We wanted to go ahead now for millimeter wave communication rather than going ahead with just conventional microwave. Semiconductor technology also has to improve. This is somewhere where I would actually like to talk of when I towards the end, when I refer to the active components. The antenna beamforming techniques are extremely crucial, and full and flexible duplex communication. Full duplex is not a problem that we already have been able to get, but flexible is definitely something which we have to look up for. So we are looking for flexible electronics, we are looking for weird electronics, we are looking for wearable electronics, and a lot of different conformal electronics, conformal antennas. We're looking up for multiple set of things now. So when FCC was initially struggling, they had given the debate was actually between two set of frequencies, either to come up at around 28 gigahertz or for sub 6 gigahertz. But with the millimeter wave range, which is typically on 28 gigahertz, there were several free space loss, a very severe free space loss that will actually come into picture. Why? Because free space loss will be lambda by 4 pi d whole square. So obviously the lambda is now also increasing. The lambda is significantly decreasing, but the distance at the same point of time will also decrease. So that will actually increase my free space loss, the degraded SINR, and that would actually mean that in order to counter almost all of them, we need a very, very high gain antenna with extreme directional beams. And that beam also has to be, steered at the same point of time. It's not that easy that we want a very, very strong, steering. So electronic steering not possible. We have to go for some digital steering techniques. So what we then come down to is narrow beams that we have to form. That means extremely high gain antennas. So a conventional antenna theory says that if you want very high beam, if you want a very narrow beam, which is a very, very high directivity, then obviously you have to go for a very large aperture, right? Because gain is 4 pi AE by lambda square. That means the effective aperture area of the antenna has to be very large. To create an effective aperture which is large enough, I need to increase the physical size of the antenna. So the question remains, how large can this antenna aperture go, and how far can you actually take it? That is where we are going to question it. So another set of a thing which we wanted till 4G, we did not face this much of a problem. In fact, till 3G and 4G, we now want a multi-beam antenna. So at the same point of time, the antenna should be able to cover up almost all the different set of users. Whereas in the previous case till 2G, we were getting only one particular antenna which was covering the broad coverage for all the users. But now we want multi-beam antennas for 5G to roll out. And that is exactly what is being shown over here. Till the fourth generation, we had one particular area which was being swept. In 5G, because we have now multiple set of devices, we want multi-beam technology. And at the same time, this beam also has to move. That means it has to constantly track the different set of devices almost at the same instant of time, almost at the same instant. So then we actually have to move to something which is called as the phased array antenna techniques. So let's just get back, with with some fundamentals and foundational antenna theory and techniques, and what is actually needed in the phased array concept. So when we look onto any radiated fields, we have a certain reactive region, there is a radiation region, and then you've got the far field region. All the boundaries are typically given by the near field region, which is one is the Fraunhofer region, the second is Fresnel region. So we very well classify it by virtue of the distance. At the far field region, obviously, the wavefront now becomes normal. So it is independent of the angular perspective. It is now only a function of distance that you eventually get, right? So this is exactly what is being shown, what is being actually shown over here. There's one base station 8 element array at 2.7 gigahertz, and so we have been able to do all the different field measurements. So at far field distance, the wavefront becomes almost plain wavefront, whereas in the near field distance, if you so observe, what we find is that there is a constant phase change which is taking place, a very fast phase change which is eventually taking place. So, whenever it comes down to near field, we need to talk of both the phase as well as the magnitude. So, the electric field vector will be now moving as some amplitude or some magnitude e to the power of j omega t e to the power minus j beta z. So, it is going to oscillate very, very fast. But when you talk about far field, we are now only referring to the magnitude. So if you have gone to the field also and checked out, we simply use a power meter, and in the far field of the antenna distance, we can simply measure that this is the exact power level that we are getting. Magnitude, that's it. That's more than important. That's more than a complete comprehensive information that we have. So what is the trouble? I'm taking one DUT, which is some device under test, which is some user equipment, some laptop, some small cell base station, and some macro base station. And if I compare the size of this DUT remaining the same, the physical size of the DUT remaining the same, at cellular level, which is at 2.7 gigahertz, what we observe is that this far field distance would eventually become zero point 0.3 meter. The same UE becomes the far field for 28 gigahertz for the same physical size will now become 3 meter. Same way, if you compare something for a DUT of just 1 meter, the far field distance in 2.7 gigahertz was 18 meter, and the far field distance at 28 gigahertz becomes 187 meter. Now that is something very interesting. So I post a question over here, and in fact, just out of a small interaction, uh, how many of you have actually seen any anechoic chamber, and what is
Yeah,
typically the size of the anechoic chamber
sir,
that you
your
come across?
voice was not clear.
Uh, is it better off now?
Ah, yes, sir. Yes, sir.
So what I was asking is that has anybody seen an anecho? How many of you have actually done anechoic measurement chambers, anechoic chamber measurements? And what is typically the size of an anechoic chamber? As just an introduction, as just a query, it is typically of the room size. Very good, I get a wonderful answer. Typically of a room size, yes. A full blown anechoic chamber will be typically of the room size, which can be almost like 20 feet by 10 feet by 20 feet. That's one of the things that you can actually come across. Excellent, so we'll go ahead with that. So if I now again go back, if I now again go back, when I was doing a conventional anechoic chamber measurement at cellular level of 2.7 gigahertz, typically 18 meter was possible. But now if I want to do it on 28 gigahertz for the same chamber, will that be possible? No, because the far field distance for the same components that we were actually using, the physical sizes, obviously they are now moving out of bounds. So any small macro cell base station of 1 meter physical size is now having a far field distance of 187 meter. That's quite large. So what do we do? Best thing is what we can take a solution out of it, which is you take a Fourier transform of the near field, and then you can do the far field measurements. You can extract the far field information of it. That is one of the way in which we can do this particular measurement. So when it comes down to all these set of a problem, we find a solution, a potential solution. Instead of taking a larger physical size, let's talk about the array, and let us make it even more versatile by adding a phased array concept to it. So how do we go ahead with a simple array? We try to map the far field distances, which is with some delta of phi. We will try to create the distance d. We will optimize the distance d, which is the inter element distance, and we will also provide a certain phase shift which is provided by this delta phi, that is 2 pi by lambda d of sine theta. Right, if we are able to continue, if we are able to control this particular phase through the phase shifters, and we can provide, the reason of connecting the attenuators is what kind of an amplitude, whether you want the distribution to be Binomial, whether you want it to be Chebyshev or you want it to be uniform, that can be taken care of by the attenuators which are connected. So then we can get steering of the beams. That is one of the things which we can actually go ahead. So this is a simple example of a simple two element array which is generated by a simple horizontal pole. So the electric field is generated as a function of cos theta. If you now add up both of them, which is the field because of the first element and the second element put together, then we get the total field, and beta is typically the phase difference between each of the fields which we are now getting. So one will be an advancement in time, the second is going to be a delay in time if we look at it from the time perspective. So again, if you now further extend the same towards the far field region, for the phase terms, we can reduce it to r minus d by 2 cos theta, and one becomes r plus r is equals to d by 2 r plus d by 2 cos theta. So one is retarded and the second is advanced, right? That is what is happening between the phase terms for the inter element spacing which we are providing, and the amplitude terms remains almost the same, which is typically the r. So the total electric field, or the total the field which we are now getting, is typically given by the single element radiation pattern multiplied by the array factor, and this array factor is now kd cos theta plus beta by 2. So I will be able to now govern the steering of the beam by just governing this particular beta, the value of this beta. So we have an inter-element distance which we are going to fix. But if I can change the phase by virtue of the phase shift, the antenna radiation pattern can now change. The complete radiation, the beam can now be steered without physically changing the antenna. Without changing the antenna, we will be able to now steer the complete beam. So this is one of the small examples that I leave at any point of time. People can actually read it also, and they can just find out that typically what are the nulls that we are going to get for a simple 4 element. It is actually being plotted over here. This was, I had actually, just to save time, I'll just go ahead and talk about something which is more relevant and prudent. So what we follow as a practice is that for 5G, what we are now trying to look up for is, we have to come down to the active aperture antennas. And when we are talking about active aperture, the new devices, what I just said, that the semiconductor devices are to be replaced by certain components which are which are rather of importance at this sub 6 gigahertz or maybe at 28 gigahertz. We have to look up for those kind of components. So a typical linear array will always have different phase shifters and attenuators connected. And when we are looking for the beam steering part, in that case we will also add up another thing, which is the variations in all the different phase shifters. So that is how we will be able to get the beam steering at any point of time. So one of the extension of the same is an n element array, so that the gain can significantly increase. So now that will solve me the purpose of the narrow beam which we are looking for, because narrow beam has to be connected on every individual device which is to be connected. And at the same time, I'm looking for the steering of the beams which can be controlled by the phase shift. So again, if I go ahead with the complete array factor, it turns out to be a very classical expression, sin n xi by 2 upon sin xi by 2, where psi is equals to beta d cos theta plus delta by 2. So we have this very classical expression. The beam also, you get which is absolutely which is altogether normal to it. And the only trouble is that we will now start getting certain nulls and certain side lobes. That is one of the only trouble that we will now get. And the moment you take a Fourier transform of any aperture, the aperture theory in fact tells us also that if you take Fourier transform of any physical aperture, we will always get certain side lobes. So either the size of the antenna is much smaller than lambda, then you will not get a side lobe at all. That is, much smaller means it has to be very, 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 very small, typically close to 0, then you will never get a side lobe. Or if you get a very high, if you do not get a side lobe, the getting a very high directivity or a narrow beam is extremely difficult and challenging. So when we look up for broadside array, we can go ahead with the conventional definition also, and beta turns out to be almost 0. Again, for end fire array, the theta turns out to be 0 or 180 degree wherever we want it to be radiated. And if I want a scanning theory, then this beta has to be equal to minus kd cos theta. That means every time the phase angle has to be a function of this cos theta, and it can be governed either by the d or the operating frequency, which is 2 pi by lambda, because the k is now typically 2 pi by lambda. So we'll be able to control the steering of the beams by by controlling these different severe different parameters that we come across. So we have a lot of flexibility now when we are doing a beam steering. So this is one of the examples wherein we are actually steering the beam by using for a 10 element array typically. So now what are the different beamforming architectures? When I look onto the different beamforming architectures, we've got either an analog or digital or using both, which is the hybrid beamforming techniques. So when you look up for 4G, we have a single user MIMO. It is my mobile phone and all the devices connected to it. In 5G, I can be at one place, my devices can be at some another place, and so I want multi-user with multi-MIMO technique, multi-user with multiple input, multiple output technique. So the complexity now arises. It is no more a single device which is to be connected, but it's a dynamic set of all the devices which have to be actually connected. So we want a hybrid kind of a beam forming technique. So the typical trouble is, if I look onto this particular figure, the mobile antenna, the mobile phone is receiving a certain part of the complete antenna, right? Certain part of the radiated beam which it is receiving. Rest of the part is wasted. So if we have a very narrow beam now, then we are not wasting the power. We are wasting, we are in fact able to save the power level, and we can effectively connect all the respective devices, right? So that is one of the things which we get when we go ahead with the array technique. So either we talk about an analog beam forming wherein we are physically moving the complete beams, or we go for digital beam forming wherein we can actually do the complete change of the phase shift, or we can use both of them, which is analog plus the digital part, which actually gives us to the hybrid beam forming, typically all the hybrid beam forming. So in the analog system, the RF chain is completely being modeled. It is connected with all the different attenuators and phase shifters, everything all being connected. The only trouble is that there is only one particular RF chain in which all of them are actually connected. So the one RF chain would be the power amplifier, the low noise amplifier at the receiver, and filters. Everything connects on only one RF chain. That is one advantage that you get. The disadvantage would be the loss, typically, because you are cascading so many components. Interestingly, the moment you connect one mixer, you are getting a 6 dB loss. So that is one of the trouble that you get with analog beam forming. So this is one of those examples where it is actually connected with certain different wave fronts. The trouble is that if when this wave front now falls on this array, we are getting a different phase every time. So that is what is actually being shown. There is a d sine theta phase difference, which eventually you are getting from the first antenna element to the last antenna element. So we have to ensure that the correction factor for the beam, the wave which is impinged on it, is taken into account, because now this small phase will also give me a very significant piece of information. So I have to ensure that the phase of this wavefront remains uniform with the complete aperture. That should not actually change. Digital beamforming, when we are actually looking for, is now every chain becomes independent, right? So they are typically connected with most of the CMOS components. That is one thing which has been deployed also. And for 6 GHz, it's a very very popular technique, wherein most of the 5G services are now being rolled out also. And hybrid beamforming is that you can use a combination of both the analog as well as the digital beamforming techniques. So when you look up for multi-beams, this complete passive multi-beam antennas again can be divided into three parts. Either it can be reflector based, or it can be lens based, or it can be based on some beam forming techniques. So when you look up for any reflector array, we have a very conventional parabolic dish, or a or quad part of the parabolic dish, or maybe a lot of time, I don't know, many hyperbolic as a feed is also being used. Horn as a feed is also typically being used. Hyperbolic feed misalignment might generate me a phase difference, so we go ahead with a typical horn antenna feed. And the same thing goes ahead with the quadrature of the parabolic dish also. You can go ahead with a simple quad feed also. This actually gives us the Cassegrain arrangement, which is with the subreflector as a hyperbolic feed, that is typically being used in the satellite communication quite significantly, because we want a point-to-point coverage. We want maximum coverage angle in the satellite communication, so that it's already being deployed over there. Same way, when you go for the planar reflect arrays by the different antennas which are eventually being connected, the complete array with the phase differences being given, there also we can use these multiple horn antennas to get beam forming. That is another set of a thing that is for the reflect array which when we are generating. Or we can also use typically the lenses. This is a very conventional technique which is typically used in optical nano antennas, wherein you can change the direction of the beam depending on the kind of a lens that you are using. Mostly the convex lenses are always used, or maybe a fisheye lens, a half wave fisheye lens, which is very popular in the steering of this complete beam. And same way for different planar antennas also, we can produce for an n element array. The same thing can also be explored accordingly. Extension of the same, we can also work out with certain feed arrangements. So one of the most popular set of feed arrangement is Butler matrix. So Butler matrix is typically wherein we can get multiple set of multiple set of antennas being connected to the different transmit and the receive ports, and all of them can get a different set of an angle. So you can also get a multi-beam antenna over different set of angles by using a simple Butler matrix. The only trouble with a Butler matrix is size. It is going to occupy a lot of space when you are actually applying it on multi-beam antenna techniques. So the extension would be now multi-beam antenna and connected to the phased array antenna. So I want that is where we were talking about when we introduced the lecture. When we were at the introduction section, I said that we want multiple devices to be connected, and steering of those beams is also needed. So the solution that we have to now come up for an architecture when we're rolling out for 5G and 6G is multi-beam phased array antenna. So we have to look up for the complete combination of this whole, which is the hybrid form along with the multi-beams. This together has to be integrated as a possible solution. So this is one of the system level architecture of this active multi-beam antennas. So the moment you talk about this multi-beam and phased array antennas, we need some important active components. So there is some trouble with the active components also, which I'll actually talk of gradually, that where the active components and what is the trouble with the active component design and development. So this is all about basically what are the critical and crucial requirements in the RF and microwave front ends. So what have we actually been doing so far? In most of the things that we have done at Triple IT was on the research part was mostly on the dielectric resonator antennas, because DRs can be a very strong potential base station antenna. I'm not referring it to deploy it on a mobile phone. I'm sure if nobody would love to see a very heavy handset with a dielectric resonator antenna placed on their mobile phones. Commercially, it's not viable, very obvious. So what we generally try to look up for is a base station application, because it can be easily integrated with the complete circuit itself. So the only trouble is that these DRs of different shapes, whether that is a rectangular shape, or whether that is of the cylindrical shape, or whether that is of the hemispherical shape, they will have different set of resonant modes. So either you have got non-confined modes, which is for the non-body of revolution, or you have a confined mode, which is generally meant for all the body of revolution. When I say body of revolution, I'm referring to the cylindrical geometries and the hemispherical geometries. Achha, we can also use, interestingly, a sphere. But the biggest problem is why hemisphere was chosen as the base is when you put a sphere on a ground plane, obviously the point of contact is a single point. How do you get mechanical stability for a tangential point? You will not get a mechanical stability. So you cannot use a full sphere. So we have to come down to a simple hemisphere. So there are different modes which are all excited. It is quite evident that when you have different set of modes for the different set of dielectric resonators, the beams are going to be different for the different set of modes. And the excitation strategy of each of the modes in the dielectric resonator will also be different. However, when you look onto the full scale analysis, the easiest of all Contrary to our beliefs that rectangular DRAs are possibly, easy to analyze, contrary to this fiction, the theoretical analysis is the simplest for a hemispherical geometry. Can somebody help me, tell me why is it that the hemispherical geometry gives us the simplest analysis? Can somebody just help me identify that? One very interesting reason, very interesting reason. Why is it that the hemispherical geometries are extremely close for theoretical analysis? They're always the simplest thing that we can actually work out with. Can somebody
Only,
just help me out by looking onto classical
only
electromagnetic?
it depends only on the radius parameter.
Okay. Hemispherical will depend on the radius parameter. Excellent. But why is it simple? Why will it actually look simple to work out with hemispherical geometry? Excellent. There is continuous boundary. That's a wonderful thing which we actually have to harp on. There is actually a continuous boundary. And why is there a continuous boundary? Because the wavefront in itself, generated by any source, is spherical in nature. So, unlike if it's a dipole, if you go back to the classical electrostats, the wavefront for an isolated charge is always spherical in nature, whereas for a dipole, we get a cylindrically symmetric wavefront only for a dipole. But most of the monopoles that you are using, most of the other antenna systems which we are actually using, they are strictly spherically symmetric in nature. And so hemispherical geometries confined to the boundaries because of this spherical symmetricity. That is the advantage that we actually get across. Right. Excellent point made. And one thing, which actually I'm pretty happy is that my audience is actually with me. Even at this late hour, they are all with me. So thank you so much. And no, I have not started off with the presentation, Professor Prabha. I'll go back to it now. I will actually go back to it. So thank you so much. So let me now go back again. Yeah. So we are back again to the resonant modes, which we were dealing with the different DRs wherein we are eventually working. One of the possible reasons when you are looking for wideband application is reduction in the quality factor of the dielectric resonators. So this is a very classical formula which was given by Bitt and Babik way back in around 1980s, wherein he said that this quality factor is a proportionality of the stored energy to radiated power. And if you look onto physical dimension, it is volume upon surface area. So if you make a perturbation on the dielectric resonator such that the volume increases and surface area reduces, or if I say that the S by V ratio increases, that is surface area to volume ratio increases, then the Q factor will reduce, because we want the volume to reduce, surface area to increase for the low Q factor. This in turn can also be achieved if the effective permittivity epsilon r, that is also decreased. So the best thing is pinching of holes. If you put, you will see that lot of people actually do perturbation. Why is it being that done? That is actually being done so that we can reduce the effective permittivity. So these are some of the classical, examples in many of those papers wherein we have actually talked of multiple set of techniques which we have actually introduced. The first one which you actually see is was a paper in the European Microwave Conference, which was a novel cheese hole structure. And the only reason of picking up was we picked up the static capacitance model. So the effective epsilon is typically a function of the physical dimension to which we are perturbing multiplied by the effective permittivity of the material which is being perturbed. So when you look onto the structure, there are only two different types of permittivities which are available. One, permittivity of the ceramic material, and second, permittivity of free space. That's it. So the epsilon effective becomes a simple function of both, and so we are getting a reduced effective permittivity, giving us a wide bandwidth. That is actually improving the bandwidth. Or there is another way in which we can actually work out, that is Interestingly, if you connect an antenna to the ground plane, what happens is that the surface area which is in contact with the ground plane, whatever current density is generated on it is flushed out, because the ground plane is acting as the return path. That's the flush part. So anything which is in connection to the ground plane, the complete current density associated to that is zero. If that is so, then we are losing maximum part of the current which needs to be decoupled from this particular antenna element, and it has to be radiated. So what we do, reduce this effective area. That is what we have done in the second case, which is the cup shaped geometry. If you reduce this contact area, then more and more current from the feed gets coupled into the dielectric material. This more and more current will now get decoupled because of constant reflections at the boundary of this ceramic. And when it gets reflected, that means the Q factor now reduces, so the bandwidth increases. Either you use this technique. However, for this particular part, you have to ensure that there is a strong mode matching which takes place, and that's why you cannot use impedance matching, but it is strictly mode matching technique that we use over here, so that the modes remain intact. Third is, when you perturb, we can reduce the effective impedance, input impedance, which is offered, or using multi elements. So the key strategy of wideband, and antenna techniques in the dielectric resonators can be either through perturbation or merging of different set of modes. These are couple of things which we can actually work on. If you want to improve the gain of the DRS, if you want to improve if you want to improve gain and directivity over the different set of bands, again multiple set of things can be investigated. You can use you can work out on the fact that perturb those particular areas which are not contributing to radiation. Now when you are doing so, physically, if you remove now some part which is not contributing to radiation, we are increasing the effective area. If you are increasing the effective area, gain is increased. Or there's a very popular thing which is coming up, which is you create a fabric cavity using metamaterials or meta surfaces. This can be done at both the near field as well as at the far field region. We can either do a near field loading with a simple SRR, or we can do some far field loading of different metamaterials. They will act as small fabric cavities, and that will improve us the gain. Third, another way wherein we have actually used is a partial fractal technique that is typically used again in order to create multiple set of iterations and get an improved effective aperture. Or fourth is, you can also integrate it to some horn, because horn antennas are supposed to give you a pencil beam radiation pattern. If you integrate the DRs with the pencil with the different set of horns, then also the gain can typically increase up to 14 and 17 dBi. In fact, in our lab we were able to get typically a gain of 20 dBi, that we were able to actually establish using the metamaterial as well as with using the shorted horn. We were able to get a very high gain. The third part, the third and important thing is, when you want the complete component, antenna component, to be integrated, they have to be compact in nature, and it should also have a low profile. So when I say low profile, that means the size, the width of this complete, or maybe I should correct it, the area should be much larger compared to the height. And typically the height, if it is less than 0.5 of the lambda, that's the electrical dimension, then we can get a low profile dielectric resonator. So again, there are multiple set of compact and low profile DRS which we have actually established also over different set. When you want to talk about compactness, compactness does not mean that you're just making the size small. Compact also means that you have a certain reflected plate which you are actually putting up as an extension of ground plane, or maybe as a reflector. Only then it actually adds to compactness. So the definition of compactness is a little different than making things small. So when you make it compact, because there is a conductor element in most of the systems, integration with the system becomes easy. Packaging of the system becomes easier. That is why compact antennas and compact DRAs are being taken care of. So let's say I'm taking the first example, wherein you can actually see this compact bicone geometry over here. Now, this part where I'm actually moving the cursor, you can actually see that this is an extension of the ground plane. So one side of this bicone geometry is typically connected to, this is connected to the ground plane. So there is an edge. This technique is typically called edge grounding. Same way, if we go ahead with another fractal technique wherein we are reducing the height as well as the width of the semi cylinder that we are using with every iteration, and we rotate it at the same point of time, then also we can get a very small compact geometry, which is typical, a very low profile geometry. That is one of the things which is being explored. Or at the same point of time, in order to get a compact and a low profile geometry, was when we investigated a simple Fibonacci series based antenna. So a simple Fibonacci DRA over a simple FR4. I'm referring to these case study 2 and 3. Both of them are made up out of FR4 antennas. They are not made on ceramics. So typically on FR4 materials, we were able to get low profile antennas, so that we could integrate it with the system. Or we can also use multi-element. We can also use multi-element systems wherein we can get a very compact geometry. These are different methods in which we can actually get compact and low profile DRAs. And one of the most popular things which which is being investigated is fractals on the different set of geometry. So why fractal? When you actually investigate fractal, it gives you a very systematic perturbation over the edges. So the current path, when you are doing the fractal on, let's say, a planar antenna, then you are perturbing the current path. And when you are doing a fractal on the dielectric resonator, we are actually creating the perturbation, or this continuous perturbation on the fields, typically on the different fields. So what I've actually plotted, actually, which you can actually see, is the fields, the scalar projection of the different fields, right? These are the different set of fractal antennas which are taken care of. Biggest challenge, although you can see in the second case study wherein we are using two different fractal geometries in order to improve the gain and the bandwidth, we are predicting the modes also, which can be evidently seen. Let's this first figure is typically a TE11 delta mode excited on the rectangular DR. And for the second, you can actually see TE12 delta, which is being excited on the DR. The biggest challenge while working out with the fractal geometry is modes. You don't get a modal stability. The moment you are perturbing the edges, see, it is the edge which is actually radiating or contributing to the radiation part. So if you now change the edge only, if you are changing the perturbing the edge, the biggest problem is how do you predict which particular mode is excited and what will be its consequent radiation pattern. That becomes a very, very big challenge. Whether that is a planar perturbation, whether that's a perturbation on the planar antennas, or it is a perturbation on the three-dimensional dielectric resonators, it always remains a huge challenge. Now, I'm coming to the last part, which is basically the active components which we actually need to study. So we have, taken care of almost all the different frequency sets, all these antennas. I've put the references also, which you can go through. They are all operating on different, set of frequencies, which can be well deployed for even 4G and 5G services and beyond. The biggest challenge which actually remains is how do we go ahead with the design of the active components. So now let me give a very, very clear and a very honest submission at this point. The submission is, don't ask any microwave fellow what exact device you are using for the active component. Don't ask, because that is not my aim. For that, we have a very strong fraternity of we have got a wonderful set of friends from microelectronics who are contributing to it. And that fraternity is typically your whether they're working on gallium nitride, whether they are working on BJTs, whether they are working on MOSFETs, whether they are working on JFETs, whether they are working on narrow channel, short channel, whatever they're working on, it is, the device is already being taken care of by them, and it is also equally characterized. So that's not a problem for us at all. Those things are already well taken care of. What is my concern then? My concern is a couple of set of questions. Number one, when we teach, when we actually teach that microwave for the first, or maybe let me go back, electric circuits for the first time, electric and electronic circuits for the first time, we teach them the concept of resistance. And what do we start off with? The very fundamental Ohm's law, which is V is equals to IR. That is how we eventually start off. So everywhere when you are doing AC or DC circuits, that's what it actually continues. The power is typically P is equals to I square R. The power is V square by R for the circuit, and it is always a lossy element. Excellent, interesting. The moment you talk about microwave beyond electromagnetics course, when we talk about microwave, we come across a new set of device, and that is called as negative resistance device. And what is negative resistance? The current is not following the proportion of the potential. If you apply a potential, current is decreasing, for it is decreasing in the form of some valley for one particular region. So you, if you take the projection now, it now becomes minus of R. So you are now getting minus of V by I, which is minus of R. And we are, and it is not a hypothetical concept. We have got devices on it. Gun device, all the transit time diodes, gun diodes, and all the transit time diodes. What are the different transit time diodes? Barrett, Trapat, Impact. All of these diodes, they are typically negative resistance. So the biggest question is, when you take the Smith chart, where do you actually find these negative resistance? And if there is some negative resistance which is generated by the active component, how do you actually plot it on the Smith chart and then do the so-called very, very gracious impedance matching? How will you do that? That is where my struggle lies. Why? Because if the resistance is negative, reflection coefficient is obviously, is imaginary. Reflection coefficient is no more in the bounds of the short circuit and open circuit. So what do we do? Where do we go? So we go back again to the classical Smith chart, which is where I'm going to point out the troubles while working out with active components, and how it has to be also dealt with in our millimeter wave components at the same point of time. So when we look on the Smith chart, I'll be just closing in about another 5 or 10 minutes. I hope I'm not going late, madam.
No, sir.
Yeah, thank you. So I'll be just taking a couple of 5 or 10 minutes more, then we can open it, create an open house for discussion. Smith chart is typically a bilateral transformation. So it is, if you look onto the gamma, which is the reflection coefficient, which is R plus JX, if you map it onto, if you now create a family of circles of it, we eventually get the complete Smith chart out of it, right? That is what we are actually getting, right? So the gamma is now z minus 1 upon z plus 1, where this small z is eventually normalized as r plus jx. And this gamma in itself is a function of gamma r plus j gamma I. So now when you take gamma r is equals to gamma r plus j gamma I, we will get a complete family of circle for the real value of the reflection coefficient as well as for the imaginary part of the reflection coefficient. Once you do that and map it, you will get a Smith chart, which is typically given on the right. So it's a bilateral transformation, right? Now, when you do a bilateral transformation, what we see is only this part, right? Wherever my cursor is moving from -1 to +1, and from plus j to minus j, the center part being 0, which is gamma is equals to 0, or we also call it the point of matching. So if I have to match, let's say at 75 ohm, anything and everything gets mapped at the center. If I'm matching at 50 ohm, again, it is the center. Irrespective of what value, the normalized value is always the center. That is what we come across. If you extend the Smith chart, this is what I get. The Smith chart does not end here. What is served to us on the printed paper is exactly what we see, but actual Smith chart is this. The radius can be minus 0.5, it can be minus 0.25, it can be minus, can be anything. It will always extend. Same way the circles on the other side will also extend. It does not reduce only to one part. What we see over here is this. Now, why is it so? Whenever we talk about any planar component, planar passive component, I'm strictly using the word passive component, it can be terminated either as a short or an open. So the gamma turns out either as -1 or +1, and it will oscillate between these values only, -1 to +1. So whatever we see on the printed Smith chart is exactly this. But actual Smith chart is this, which was actually beyond the one which is printed. That means I can have values of gamma, which is mod of gamma more than 1. for the negative resistance devices, which is very possible. When I say mod of gamma more than 1, what do you mean out of that? That gamma can take a value of either more than +1, or gamma can also be a value which is less than -1. So where is that particular region? This outer part, the complete outer part, is that complete region where the gamma can now be. It can be at any particular place. It can have even any particular random value. How do we go ahead? So the classification is, what you see as a printed Smith chart is for the passive devices where gamma L is less than 1, and for anything which is outside that is typically gamma L greater than 1. So that is where all my active devices lie. So the problem is, my practical Smith chart is the one which is served onto me onto the paper, is this passive part. How can I bring something which is negative inside this? The problem lies over there, that how do we actually do it? So let me go back to the classical problem of how an amplifier is to be designed, or you can extend, once you do the amplifier design, you can actually do it for any particular active component that you have to actually come across. For us, I again come back to my statement which I made. Don't ask me what is the active component. Don't ask me what kind of a biasing. That is well understood, that whether I want a class A mode of operation, or class B mode of operation, or class C or class AB for the power amplifier that I'm trying to design, that is already thought of. When I'm doing an LNA, I'll generally preferably go for the full phase coverage with the class A, right? And power amplifiers can go for any of the other classes. So I can, that is all understood. It is also expected that microelectronics people will actually give me that this is my gallium nitride based some transistor, this is possibly some HEMT, this is possibly some MOSFET, whatever it is. For me, it's a black box which I'm representing by this central part called as the transistor. I don't know what it is. It can be a gun diode, it can be any of the impact rapid barrier diode, can be anything. What is of my interest is that how do I match this particular transistor with the input and output end? This was not a problem with my passive circuits. Why? Because we were doing only one part of the matching. But now we are talking about matching at the input as well as at the output end. And we also expect that this input network is further connected to a source and the output network is further connected to a load. Interestingly, if you observe, the gamma which is now generated is not only by looking at the inside the input matching network, but also along the transistor side. Same way, when you look onto the output part, not only just the output part, once again, when you look up from the output to inside of the transistor, there is another gamma which is generated. How do we actually match them? That is where lies the trouble. So this is exactly what this black box looks to me. The transistor will have a certain S parameter, and we have now 4 different set of gammas which we come across. A gamma S when I look onto the source part, connecting when I'm looking towards the source. Gamma in when I'm looking from the input side inside the active component. I will not call it transistor alone, can be anything, but I'll call it an active component. Same way, gamma L will be generated when I'm looking towards the load end, or a gamma output, which is when I'm looking towards the active component from the load end. So there are now 4 different types of gammas which I come across with the S parameters of that particular active component already given to me. So the question is, how do you select this gamma S and gamma L? Because what I understand, that this gamma S and gamma L are now values which is mod of gamma S or gamma L more than 1. So one of the simplest preliminary answer to get maximum gain is that these gammas have to be the complex conjugates of each other. They actually have to be conjugates. And this makes life, easy. Why? Because whatever is the gamma which is outside the Smith chart, the moment you now take a conjugate of it, it moves inside the Smith chart. And so once I know this gamma in star and gamma out star, I can easily do the impedance matching now. Life becomes very easy. So I will do all the matching with reference to this gamma star, that is gamma in star or the gamma out star. And so the condition of stability for this particular active component to operate in a stable section is that the effective impedance at the input end or at the load end should always be a real quantity, that should not be imaginary. What do I understand out of it? That means whatever is the imaginary part of whatever is the gamma that I'm getting, if by virtue of the impedance matching, the total impedance is a real value at the input and output end, that means it is now a stable amplifier or a stable active component that I have generated. And unconditionally it will remain stable if the input impedance and the output impedance, when you're looking to the active component part, is always real in nature. The worst case, obviously, when you have got either a short circuit at the ZS and ZL, that's very obvious. It's very difficult to get, because if you go back to again electric circuits, when we teach our students maximum power transfer, we tell them that the maximum power will be transferred when your input and the output impedances are conjugate of each other. That is what we teach them. But if you have a short circuit as a load, then if you go back, when you look onto the power transfer ratio, this complete statement is somewhat violated. We need an open circuit for the maximum power to be now transferred. So ZS and ZL equal to 0 are my worst case for matching, typically for matching, right? And so this complete reflection coefficient, following the critical parameters of the gain that I'm trying to look up for, either I'll operate it on maximum gain or a value which is lower than that. When I look onto that, I'll get some.
Hello, sir. You are not audible. Hello, sir. You are not audible.
Hello, sir.
Sir is joining again. I think
Okay.
some network problem is there.
Okay, 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 ma'am.
Participants, just please wait. Sir is joining again. Some network issues from his side. Yes, we are sharing feedback link in some time. Please wait. Yes, sir. We are sending the feedback link in some time. Please wait.
Yeah, sorry. So it just got disconnected. I'm very sorry.
It's
So
okay, sir. No problem.
I'll just start up from the point where we just left. I'll just do the screen share again. Yeah. So is the screen visible now?
Yes, sir.
Yes, sir.
Yeah. So I'll just go ahead. So when we look on to the reflection coefficients which we have generated, and when we look on to the family of circles, we get a certain center and radial point. And why am I not getting the full screen mode here? Okay. So we get the complete family of circles where we will now operate. And why is it? Okay, so we will now get the detailed family of circles corresponding to whatever gain that I'm trying to measure. And like I said, that the gamma is going to be now a complex conjugate of this input or the output reflection coefficient. And so if you look up for a simple unilateral case that I've just taken as an example for an unconditionally stable amplifier, this gamma I turns out to be now SII star. So whether if you're looking for the input side, obviously it is S11 star. At the output end, it will become S22 star. That is what will eventually the gamma is. Whatever is the S parameter given to me, accordingly I'll be able to get this value of the input. So one of the ways of locating this gamma star, which is my reflection coefficient, complex conjugate of the reflection coefficient, will be whatever is the value of z, find out the negative z, then do a simple inversion of minus of z star, which is 1 by gamma star. And that is by doing a simple multiplication over the numerical and over the numerator and denominator, which is normalization. And through that we'll be able to get the value of this gamma star, which is the reflection coefficient or the complex conjugate of the reflection coefficient. So accordingly, once I have found the value of the stability circle and I have found what is my operating value of this respective reflection coefficient, I can simply do an impedance matching. And with this, I'll be able to now get this impedance matched network for a simple, unstable case. This now can be done for any particular frequency, whether you are looking for a frequency of, whether you are looking for, let's say, the frequencies of millimeter wave, or you are looking for RF and microwave frequencies. Anything that you try to deal with, you'll be able to do a simple design using any of them, typically with any of them. Right. So with this, I close my, in fact, talk, and I just I'm open to any questions that the faculty members have. We can take one by one any of the questions. My sincere apologies that my video is not working. I really don't know why is it not working. I tested today in the office also. That time also it was okay. But my sincere apologies that it is really not working, because it becomes a one-sided, kind of a thing.
It's okay, sir. No problem.
Yes, so we can take questions, ma'am.
Yeah.
As moderator, you can just.
Palash Kundu sir has raised their hands. Please unmute. Yes, Palash sir. Any query? Sir, you can unmute. Jayalakshmi ma'am, please mute yourself. Jayalakshmi ma'am. Yes, Jayalakshmi ma'am, please mute yourself.
Chintan sir, please mute him. Mute her.
मैम मैं होस्ट में नहीं हूँ. मनीषा मैम
Already
उनको
done.
बोल-
Done.
हाँ किया.
Yes, Palash sir, can you just unmute yourself? Whatever query you can talk with sir. Sir, you can paste it in chat box if it is not possible from your side. Yes, those who have any questions, they can ask.
My professors who've actually taught me used to always tell me one thing: if there is no question, there are only two interpretations. One, either the lecture has been, phenomenally good, that's why everybody is understood and nobody wants to ask a question, or second, I do not want to comment on it beyond.
The lecture was very nice.
No, no, no.
Everybody
That's
understood
absolutely
everything.
okay, ma'am.
Let us hope for the first option, sir.
Yes.
I really hope for that.
Yeah.
I
So
really hope for that.
you're getting reply that the session was very
Yeah.
nice.
Thank you. So we can always, my contact details are also available at any point of time. Anybody wants, contact, they can always, get back to me.
Mugdha
There's
madam,
one
there is a
question I
question
actually see. What is the
from
role of
Jogesh
the
sir.
precoder in the millimeter design? Now, when you're looking for the precoder part, actually, Professor Devidas Chikal is actually asking for it. Precoder again will be a part of the communication strategies. So it is basically the communication people and strategists who are actually looking for the precoders. So they are what we people are actually looking up for is the hardware implementation, right? We are looking on to, so that can either come down either to your solid state devices or to your respective phase shifters, wherein we want it to be an integration in terms of the size. But when you're looking for the precoder very specifically and what kind of are the requirements of the precoder, that I think the communication people will be able to actually tell you, looking onto the massive information and the data which is generated. So that actually would actually come down more towards communication side. Millimeter wave design, it is more of into the either the active component part, wherein the microelectronics people will help us sort out the problems of the kind of active component we are using. We again as RF and microwave engineers will be more into looking onto the matching networks for this part, or it can be the passive components along with antenna components, which eventually has to be taken care of. Signal processing and pre-coding will be a part of mostly into the communication sector. I hope that it answers the query.
Yes, any other questions if you have, you can paste it in chat box or you can unmute and ask your questions.
By that time, we can click a photograph, Muda.
Yes, ma'am. Yes, ma'am. Yes, all participants are requested to switch on their cameras for photograph.
Yes.
Okay, I will take now. All are ready? Done. Thank you.
Okay, ma'am. Sir, there is one more question. General examples for pre-coding.
So again, that will also come from the communication strategists. They will only be able to actually tell you what pre-coding techniques are typically to be deployed for the communication strategy. That will again, come down from them. The communication people will be rather more, clear about what kind of a thing. At the hardware end, because we will get everything integrated and we have to put it into directly into the casing and packaging part. So that is why pre-coding will rather not be of more importance to us on the millimeter wave. So communication strategist people will be able to clarify that. As I can actually see that you have got some communication people also talking about how the signal processing or how the communication is to be interpreted. So they will be able to actually tell you the pre-coding examples over there. We will actually mostly look onto the RF and the RF microwave part or the hardware part of it.
Uh, any other questions? Anybody have? Sir, I think there are no questions because everybody understood everything. What we Sir,
Right.
can we proceed with the end of the session?
Yes, ma'am. You can.
Yes.
We can. It's
Yeah.
absolutely at your end. We can go
Okay,
ahead.
okay. Thank you so much, Dr. Biswajeet sir, for wonderful and informative session. I'm sure participants must have got deep insight of millimeter wave communication system for 5G. Thank you so much, sir.
Thank you so much, ma'am,
Thank you, sir.
for having invited. Thank you so much, ma'am.
Yes, sir.
Really an honor. Next, I think Jogesh Dash is taking over.
Yes, sir. Yes.
So he'll join in the same link only.
Yes,
Yes,
sir.
sir.
Same link.
He has
Okay.
joined, sir.
He's joined.
Yes, sir. Yes, sir.
Good evening, Jogesh. Jogesh happens to be my, we are from the same lab, in fact, of IIT Bombay.
Good
So,
evening, sir. Good evening, sir.
good evening, Jogesh. I'm so sorry I cannot turn on my video, Jogesh. The laptop is giving me a trouble today for the video part. So I'm so sorry I cannot, wave you also. But
Fine,
welcome
sir.
aboard.
Fine. I can see you are waving.
But it's really an honor to share the stage with you, Jogesh. It's really an honor.
So this is my honor that I am sharing the stage with you, and
Really.
I'm feeling also privileged that uh, my senior and the same lab mate, we both are presenting in the same platform. I'm feeling also privileged.
Yeah. That's a huge honor. That's a huge honor. But thank you so much, Dr. Bala and the complete team for this wonderful organization. Thank you so much.
Thank you, sir. Thank you so much for joining us.
Thank you.
And looking forward to see you in such sessions again, sir. Thank you.
Sure.
Thank you so much.
Thank you, ma'am. Thank you so much. Bye.
Welcome, Dr. Jogesh. Yes, Gaurav, sir, please go ahead with the session.
Yes, all participants are requested to fill feedback form for the first session, the link for which is posted in chat box. Now let us proceed for day 3 session 2. I would request Gaurav Tavade sir to take over.
Thank you,
Yes,
Mugdha madam.
Yeah.
Yeah, am I audible clearly?
Yes.
Yes, go.
Yeah. Good evening, everyone. A very warm welcome to all the participants and our distinguished speaker. I am Mr. Gaurav Tavade, the host for today's second session. It's a pleasure to have you all here for today's session of Atal Faculty Development Program on millimeter wave technology. It's now my pleasure to introduce our speaker of the day, Dr. Jogesh Chandra Dash, who is an assistant professor in Electronics and Communication Engineering Department, NIT Rourkela, Odisha. Dr. Jogesh Chandra Dash obtained his BTech in Electronics and Communication Engineering from Biju Patnaik University of Technology, Rourkela in 2013, MTech in Electronics and Telecommunication Engineering with RF and microwave specialization from Veer Surendra Sai University of Technology, Burla in 2016, and PhD in Electrical Engineering with specialization in RF and microwave communication from Indian Institute of Technology, Bombay in 2021. During his PhD, he has worked closely with various industries such as Coal India Limited, Ministry of Coal, GOI and Mercedes-Benz Research and Development India. He has worked as postdoctoral research associate and Institute of Eminence IISc postdoctoral fellow at Laboratory for Innovation and Development in Antennas, Radars and Electromagnetics, Electronic and Communication Engineering Department, IISc, for 2 years. He is currently working as an assistant professor in the Department of Electronics and Communication Engineering at the National Institute of Technology, Rourkela. Dr. Dash serves as an associate editor in Nature Scientific Report and a reviewer in several prestigious journals like IEEE TAP, IEEE AWPL, IEEE Access, Wiley International Journal of RF and Computer Aided Engineering. He has 2 book chapters, 5 filed Indian patents, and authored and co-authored 50 research articles in peer-reviewed journals and at international conferences. Dr. Dash is the recipient of URSC Young Scientist Award twice. His research interests include full duplex antenna design and IRS design for 6G communication, MIMO antenna design and analysis, MIMO radar antenna design and integration, study for automotive applications, antennas for wireless power transfer for biomedical applications, and electrically small antennas. On behalf of Department of Electronics and Telecommunication Engineering, Vivekanand Education Society's Institute of Technology, and all the participants from various states, We welcome you, sir, in today's session for our Atal FDP. For today, the topic of sir's talk under the umbrella of millimeter wave radar and imaging is MIMO radar antenna design, study of integration effects and its solution for autonomous vehicle applications. Participants, please note that after each session, there will be a question, answer and discussion segment. So please make sure to stay engaged and participate actively. So I request sir to start with his session. Over to you, sir.
Yeah, thank you so much, sir, for your kind introduction. So let me share my screen. Is it visible? My screen visible, everyone?
Yes, sir.
Okay, thank you so much for this opportunity to share my research on this millimeter wave technology. So I hope I am audible and my screen is visible. Just to confirm once again.
Yes, sir, you are audible and your screen is visible also.
Okay, thank you so much, ma'am. So, so my name is Jogesh Chandra Das. Right now, I'm working as an assistant professor in IC department in IIT Rourkela. So, my today's topic of presentation is about the millimeter wave MIMO radar antenna design, study of integration effects, and its solution for autonomous vehicle application. And before I go into our actual content, I would like to just highlight a few things about NIT Rourkela and our lab, antenna design lab at NIT Rourkela. So this is the location of NIT Rourkela in Odisha, where we are situated in right now. And this is our antenna design lab. So, and we are having multiple equipment such as VNA also, spectrum analyzer, anechoic chamber facility for antenna measurement, and the ground penetrating radar measurement facilities are available in our department. So this is our department building. We share this is called electrical science building, the electrical engineering department and both electronics department, we share the same building. So apart from that, in our antenna design lab, we are having some licensed software on ANSYS HFSS and CST Micro Studio also. Well, with that said, I would like to proceed for my topic of discussion today. It's about, I will start with some introduction, then brief about ADAS. It's called Advanced Driver Assistance System. Then principle of MIMO radar antenna design, study of vehicle integration of radar antenna and proposed solution, and how we have deal with this problem and how we have came across with problem and with a solution for industry application that I will share completely from end to end, starting from the problem to the solution, how we have reached, and the conclusion. So here I would like to acknowledge Dr. Vivek Dhoot, who is a senior program manager from ADAS System Radar, Mercedes-Benz Research Development India. Most of my talk will be today is on the automotive radar antenna design and integration study that I had completely done with Mercedes-Benz, and as well as also what I have done during my PhD, as well as in further research in IISc Bangalore, as well as in NIT Rourkela, based on this topic, and how we have provided one end-to-end solution in the industry application. I'll completely discuss about that, and how it will be helpful to discuss with in classroom lectures also, how you can implement it, as well as how we can provide some real-time problem statements to the students and how they can work. That also I will share. Well, let's discuss about advanced driver assistance system. So as you can see in this picture, it is an 1886 model of a Mercedes-Benz vehicle. As you can see over here, the thing is just a wheel, just three wheels are there, nothing else you can see right now in this picture. However, if we talk about the 2020 onwards model, the car which is coming from Mercedes-Benz or any other company, autonomous vehicle companies or vehicle companies. So right now it is a fully autonomous in nature with some different features that was not available earlier in any kind of cars. you can see the comparison between two these cars. The earlier model, the first car, and the car which are coming right now in our market is completely autonomous with full functionality of that, and it is due to the presence of the ADAS system, and which is providing a circle of complete safety to the car. Even if you are in a car having you are in a brutal accident, also that is helping to protect a human being inside this car. Well, so how we are getting this safety? That is because of the multiple sensors are being installed in cars, such as your radars, lidar, ultrasonic sensors, cameras, and all, which is providing a complete 3D view and a complete circle of safety that is providing to us. Moreover, as far as today's topic is concerned, I'll be mostly focusing on the millimeter wave automotive radars. So the millimeter wave radar, as we can right now we're discussing, that can be segregated in three different configurations, is called your short range radar, medium range radar, and the long range radar, and that is being classified according to the field of view and maximum attainable range and application. Means what is the distance it is covering from the car to the road onwards, as well as what is the angular field of view it is covering. It is the radar. Based on that, we are defining this millimeter wave radar into three configurations: short range, medium range, and the long range. Further, the first generation, and these automotive millimeter wave radars are being designed and used at 77 GHz frequency of operation. And the first generation of 77 GHz radar came in 1998 from the Daimler. So Daimler is a parent company of the Mercedes-Benz. Well, so let's discuss about some of the sensors technology that I have highlighted that is providing a complete safety, such as the camera, lidar, and radar. And this is just a comparison study of three important sensors that is being installed in various autonomous vehicles to provide a ADAS application, and which sensor is most important or that can provide better capability than the other sensor. This table is showing to us. If we talk about the all-weather operation capability, definitely radar is going to be the best option compared to the other sensors like camera and the lidar, because radar is using the millimeter wave or the RF technology, where the lidar and the camera, they are using the optical technology. That is why it is being obstructed by the different harsh weather conditions, such as your rain, fog, smog, all these kind of things, where the radar will be going to work at these situations very perfectly. Further, the operation range, if we consider, the camera can work from mid range to far. Similarly, the lidar can also work from mid to far, where the radar can work from near field to the far field configuration. Based on the antenna technology we are using, we can go for near field operation as well as the far field operation. Similarly, okay, next go for the angular resolution. Definitely, the angular resolution of the camera and the lidar is definitely higher than the radar, because of again the higher frequency or the optical wave they are using. However, the radar angular resolution is also good, and however, right now it is called the 4D radar that are coming into the market, that are also providing very good angular resolution of 1 degree compared to the 3D radar of which was providing earlier the 5 degree of angular resolution. I will also discuss about what is the 1 degree of resolution and all, what is angular resolution. Then ambient light independency, if you talk about, again lidar and radar are better compared to the camera. Again, because if you have the low light condition at that time, camera will not be able to capture the better information, where the radar can able to capture that. Definitely next is the texture interpretation, and where definitely the camera is going to take better capture interpretation than the lidar and the radar. Further, as far as the cost is concerned, the lidar is having the more cost compared to our camera and the radar. If you talk about all three sensors and the different application scenarios, then if you can see that radar is providing better solution or the better capabilities than the other sensors such as camera and the lidar. However, right now what is happening, that right now autonomous vehicle or the automotive industries are they are considering all three sensors combinedly to get a sensor fusion to provide more robust application. Definitely, where camera can provide a better angular resolution compared to radar, so that can be handled by camera or the lidar. And apart from the other conditions, radar can take over and compared to the camera and the lidar. So the sensor fusion can provide the more robust and the accurate solution or the interpretation compared to the any single sensor. However, radar is the most versatile sensor compared to the camera and the lidar. Well, if we talk about installation of different kind of sensors in a car, it is the one of the Mercedes Benz vehicle is of S class, which is called the conditionally automated driving in the S class become reality. So this is one car, S class car of Mercedes Benz, where you can see different locations where the sensors are being installed. Like you can see, these are the lidar sensors, the radars is also installed over here, then road moisture sensor, ultrasonic antennas areas are being installed over the top camera, as well as the driver camera also being installed. So you can see over that. So here the one word I have mentioned, conditionally automated. So I will also discuss what is that conditionally automated means, because there are various levels of automation in automotive industry, and they use based on the requirements as well as the cost difference of the cars. There are different level of conditionally or different level of safety or the autonomous vehicle safety or the classes are coming. I will discuss about it. So here you can see, as you can see over here, no. So all the sensors apart from the camera and the lidar are being installed behind a certain bumper material. So I will discuss about it, what is the problem and why it is being installed behind and why the lidar is not being installed behind. So this is very simple, that if we'll keep one sensor behind a bumper material of a car, so that will be obstructed by the bumper material. Like the camera and the lidar will not going to work in this situation. How? Because of the RF and the millimeter wave technology, the installed radar behind a bumper can work properly. However, the problem of the autonomous industry is that they want to hide these sensors inside something, because they don't want to destroy their car looks. So this was a challenge that was being going on. So however, we have tried to provide some initial level of solution, though definitely not a complete, though initial level of solution that may provide good interpretation of the data interpretation from different sensors, mostly the radar, if it is being installed. Okay, so let's go to the autonomous driving levels. As I was discussing, it is starting from level 1 to it is going towards the level 5. It's starting from driver assistance to the full automation. So where the level 1 says that human driver operates the car, but with assistance from an automated system, steering and acceleration, but not the both. Point is that here the driver or any driver has to drive the car, and the external stimuli will be collected that may not work very properly at both the ends, means driver as well as the autonomous or the assistance level. Whereas if you go towards the level 2, it's called the partial automation, where the automated assistance is offered both the steering and acceleration. Means here I'm just in level 2 they have just increased the functionality to steering and acceleration, where it was only whether it is acceleration or the steering part was working, but the driver is still responsible for the safety critical actions, because here in the level 2, as driver has to take all the actions based on the data or the information provided by the sensors for the acceleration as well as the steering only, not the others. And the third level 3 is coming the conditional automation, as I was discussing the conditional automation in the previous slide, where the sensors monitor the surrounding environment and the additional activities are being automated, such as braking. The driver must ready to intervene. Means here is that here multiple sensors will be being installed, like the camera, lidar and radar, and they will be providing all surrounding information to the driver, and it will also provide some work, like some emergency braking system also will be provided in this condition. Still, driver must be ready to take over, like if any problem is coming or that is not working properly, driver has to act immediately at that time. Okay, let's if you go towards the level 5 of full automation, the driver specify the destination and the car does the rest of its own. At this level, there is no need for the steering wheels or the pedals. If you see, as I was showing one car, it was being designed at 2020 year 2020 onwards, that the same car that you have to just like your Google Map or your Ola or Uber, you have to just provide the location. Then that you will not get any steering wheels or any pedals. You will not get anything there. You will only have to specify the location. The rest, everything the car will do. To reach to the location wherever it is required, will take turn, will apply brake. Everything will be done by the car. This is the level 5 or the full automation level. Well, so how is this being done? So what is the motivation behind it? So the motivation is that almost all the vehicle accidents are being caused by the human errors, right? And which can be avoided with the advanced driver assistance system, and that is why we are implementing all these kind of sensors like radar and lidars. So what are the different essential safety criteria or the safety critical ADAS application includes are the pedestrian detection, lane departure detection, traffic signals, automatic emergency braking, and the blind spot detection. If we will sum up everything and we'll find out, if you'll think about what is the radar is being provided. So the automotive radar is in a nutshell that is installed in a car that can provide the 4D image or the 4D radar. We can say that is providing range, velocity, azimuth, and elevation. These are the four D means the four different dimensions of the scanning capability that is being provided by the 4D radar. And the fourth dimension is nothing but the elevation dimension, which is being provided right now with the 4D radar. Earlier, the 3D radar which was being used, that was given only that was providing only range, azimuth, and the velocity. Further, it is capable of all weather operation capabilities there, definitely because of the millimeter wave technology. Then the behind the bumper installation capability means other sensors we cannot install behind a bumper. We cannot hide them because of the optical technology as camera, all the lidar where the radar can be installed behind. And further, the best range and velocity with integration only radar can provide. So these are certain advantages of the radar in a complete nutshell what we are discussing compared to the other sensors, and the point is that to avoid the human error and to provide a safety driving experience. Well, so let's move towards the radar technology discussion point of view. So what is the type of radar is being used? The radar is called the MIMO radar, and that is being used in your autonomous vehicles for this ADAS application. And if you segregate the MIMO radar, that based on the antenna placement, that can be of two types. One is the MIMO radar with widely separated antenna, which is the multi-static configuration. This is the schematic of your MIMO radar with widely separated antenna. And next is the MIMO radar with co-located antenna, which is the quasi-monostatic configuration. Means both the transmitter as well as the receiver are placed in the same platform. This is a MIMO radar schematic configuration. And this is one of the hardware, means MIMO radar hardware for autonomous vehicle that is actually being used in cars, where the MIMO term is coming means the multiple input and multiple output, where we have 3 transmitters over here and the 4 receivers. Means we have to use multiple transmitting antenna and multiple receiving antenna. So based on, you can take equal number of transmitter and unequal number of transmitter and receiver also based on our requirement. How these numbers are being also we are considering, that also I will discuss. Well, what is the advantage of this MIMO radar compared to the earlier only single radar configuration? Well, the advantage is that the waveform diversity is being provided by the MIMO radar. So what is that waveform diversity is? So the waveform diversity is to transmit multiple probing signal or the orthogonal waveform transmission. That is called the waveform diversity. Means we can transmit multiple orthogonal signals, means mutually independent signals from all the different transmitters, and so that we can also receive accordingly. So okay, so before going that, let me discuss what is the advantage and what is the waveform diversity enables. So it enables that significantly improved parameter identifiability, means that is the maximum number of targets that can be uniquely identify a radar by using this MIMO radar configuration, because we are transmitting multiple probing signals, so we can we can identify multiple number of targets compared to the only a single input, single output radar configuration. Further, direct applicability of the adaptive arrays for target detection and the parameter estimation. Since the MIMO radar transmit different waveforms on all different antennas, the differently located targets that reflects can be linearly independent to each other. Means the reflection that will coming from the different target that will be linearly independent, so that we can directly identify which target is which one. Next is that a much enhanced flexibility for the transmitting beam pattern design. That means because we have the flexibility to design the waveform and the pattern of the antenna, so we can transmit completely different beam forming capabilities from the antenna configuration that are being used in the MIMO radar. Well, so allowing each antenna to transmit an independent waveform that adds the flexibility to beam pattern design, which can be optimized to increase the performance. Means we have the complete flexibility over all the antennas being used in a MIMO configuration, where we can transmit different kind of waveforms. The same time, we can also change the beam pattern in different antennas. We can also provide, we can optimize also that. These are the flexibilities that is being provided. It's called waveform diversity, that is being provided by the MIMO radar configuration only, compared to the other radar technology or the single radar technology that was used earlier. Well, so what is that MIMO radar? How exactly it is working? So what is the principle of MIMO radar? So the principle is that, suppose we are having M transmitter over here and N receiver. And if we write the steering vector of this transmitter and the receiver, let's A P theta is the steering vector, or that is being written based on its position vector. Well, so how to write it? So we can write is that if you take the first antenna as a reference antenna, then 1 e to the power minus j k dt sine theta, and similarly it will go on. So dt is the distance between the two antennas, sine theta is the angle of departure, and the k is the wave number that we know. Well, similarly, if we write the steering vector for receiver antenna, similarly we can write h for the transmitter. Instead of a incidence or a traveling angle, you have to consider the angle of or the coming or the departing angle. It is the coming angle to the antenna you have to consider. So the capability of the MIMO radar works in the principle of the virtual array configuration that is being generated due to this waveform diversity application. What is the virtual array is that, because of this presence of the multiple transmitter and the multiple receiver, we are having, suppose M transmitter and N receiver, that is the M plus N. If you see, we have M plus N physical array, because we have M transmitter and the N receiver. If we just add it, we are having M plus N physical arrays physically available. But due to the virtual array configuration, we are going to get the M into N virtual arrays out of this M plus N physical arrays. That means what? Because of this waveform diversity, each transmitter and all receiver antenna can be coupled to the each transmitter antenna, and we can get similarly the Kronecker product between the transmitter and the receiver, that is providing us to generate the virtual array, so that the virtual aperture is now being increased, and this increased virtual aperture provides us to reduce to improve angular resolution and compared to the any other antennas or any other single input single output antenna. Well, so how exactly it is being done, or how this virtual array configuration is improving the angular or your angular resolution. So before that, let's discuss about what is angular resolution. Angular resolution defines the ability of a radar system to separate the objects as the same range and the different angular positions. And based on the Rayleigh criterion, the mathematical formulation for this angular resolution is, right, theta is 1.22 lambda by d, where d is the size of the antenna aperture. So let's the MIMO radar provides definitely widen the antenna virtual aperture, so that it provides the angular resolution. So how it is? Let's take one example. Suppose we are having only one antenna and 4 receiver antenna. So this one antenna and 4 receiver antenna, it is not defining a MIMO system, because there is no multiple antenna as a transmitter we are using. Suppose the angular resolution of this configuration having one transmitter and 4 receiver is provided theta. And if you want to increase the angular resolution by 50% improvement we want, we need to increase the number of receiver to suppose 4 to 8. Right now we are having one transmitter and 8 receiver. because the physical aperture of this complete system is now increased twice now, so the angular resolution is also reduced or the improved by 50%. Or suppose we are getting angular resolution of theta by 2. It is still right now not in MIMO configuration. Suppose now we'll go to the MIMO configuration where we'll use 2 transmitter antenna and 4 receiver antenna. Now it is a MIMO radar configuration, and because it is MIMO radar, it will work on the waveform diversity and the virtual array generation. Now the virtual array will be providing the 8 antenna configuration, means 2 multiplied by 4, providing 8 antenna configuration. So we will be getting the same angular resolution as we were getting in the previous case. So it was the smaller in size as well as the low hardware cost we are providing in the MIMO configuration, because we are reducing the 4 receiver chains over here. Only we are adding 1 transmitter section. Instead, we are reducing all these 4 receiver section that we were using earlier, and we are getting with the reduced size, and we are getting the same angular resolution with low hardware cost. So this is how it is helping us to get the angular resolution. Well, let's move towards the design of this MIMO radar antenna. How exactly it is looking like. So this is a MIMO radar configuration having 2 transmitter and 4 receiver. So you can increase and decrease the number of transmitter and receiver based on a requirement. I will also discuss if we are increasing and decreasing, how exactly it is affecting the performance. Well, and here each antenna is designed based on the binomially tapered array configuration. And this antenna designed at 77 gigahertz operating frequency. What is the binomial tapered? I will discuss again. And because we are considering a MIMO configuration, we should not ignore the mutual coupling effects also. Here, if you see, the mutual coupling between the transmitter 1 to transmitter 2 is below 20 dB, as well as compared to the other receiver, if you see, it is below minus 40 dB, which is showing a very good mutual coupling reduction between the antennas. Well, this is the field of view of the antenna, the azimuth field of view. The reason I'm showing the field of view, why? Because I will also show if this antenna is not installed anywhere. This is a standalone antenna system or the MIMO radar system. If we will install it, how it is being distorted pattern we are getting, I will show you. Well, so this is a field of view of nearly 80 degree we are getting. Okay, let's discuss about how this antenna is being designed. So what is this binomial coefficient or the binomial series fed array? So here it is the middle. We are considering this microstrip patch, which is the number 1 where it is provided. From that to 2 and onward, the width is being tapered based on the binomial coefficients. Earlier, the antennas that was being used using binomial coefficient, that were center fed antennas they were using. So here we are using the edge fed configuration. The reason to use the edge fed configuration is that, as I have already showed one hardware module, in a single platform, if you are using edge fed, we can also use a IC platform we can use, and directly we can feed we can provide the feed or the signal we can give in a planar format, compared to the center fed configuration that is little bit difficult. Well, that is why, to reduce the problem of the center feed, where we are converting to this edge feed, we are providing a 2 correction factors at the 2 ends of this binomial coefficient, and we got this antenna design at the 77 gigahertz, which was showing a side lobe level of below 16 dB, cross polar level of 30 dB below, with a field of view of 80 degree of response we are getting from this single antenna. Okay. So let's move towards to see the 3 antenna configuration, or the 3 transmitter and the 4 receiver antenna, that we are using the same antenna. So from this onwards, I'm going to use the same kind of series fed antenna configuration. Well, so, and this kind of antenna, which is only provided in a single row or a single direction, that we call a 1D MIMO radar antenna. So because it is providing only one dimension or only azimuth field of view, we are not considering the azimuth elevation over here. Only we are considering the azimuth. Because why we are using this 3 antenna, this is the position vector of this 3 antenna, which has each distance is 2 lambda to each other, and here the receiver's antenna is separated at lambda by 2 to each other. This is the minimum separation distance is lambda by 2 we have to use to reduce the mutual coupling effect between the antennas. Based on the equations of the angular resolution, if we calculate and using the virtual array theory, the angular resolution is being calculated is 5.82 degree from this and three transmitter and the four antenna configuration. This is the formula, the 1 by 1.2 to lambda by d, at where lambda is being considered at 77 gigahertz or the millimeter wave operating frequency. Next to that, recently means just in the December 2024, we published another work on the series field configuration, where our objective is to completely reduce completely reduce our side lobe part of the antenna. So why we are right now being obsessed with side lobe reduction is that if we are talking about autonomous vehicle or the radar application, the side lobe radiation may also affect our field of view. That may also create additional clutter or false alarming. So that you need to reduce the side lobes if you're considering this kind of antenna. So here we have used of new feeding technology. Instead of using only a single line feeding, we are using a feeding that is or H kind of shape feeding is used, and this kind of feeding we have is actually inspired by some earlier antenna technology. What the contribution what we have made is that we have made again the center feed configuration to our edge feed configuration, and accordingly we have modified this complete structure at 24 gigahertz operating frequency. Okay, just to give you one information that why I have done right now for 24 gigahertz, why I was earlier going for 77 gigahertz, is that there are two operating frequency at millimeter wave radar designed for autonomous vehicle. Is one is 24 gigahertz of frequency, one is 77 gigahertz frequency. Definitely, right now we do not have that facility of 77 gigahertz fabrication and measurement. So we can go for our study purpose, we can go for 24. But right now the autonomous vehicle industry are now using 77 gigahertz frequency. There at that frequency they are using a reduced design and high angular accuracy, because the high bandwidth they are using at the higher millimeter wave frequency. Well, at this design of 24 gigahertz, we are getting a side lobe below minus 23 dB compared to the earlier that was only giving the 16 dB. Well, further then again we move towards the MIMO. The single antenna is being converted to the MIMO configuration of two element, which is called the traditional configuration of the MIMO, the traditional MIMO configuration, where we are keeping serially transmitter and receiver in a different place, completely different segment, and where this configuration is called the sparse MIMO configuration, where the receiver antennas are being placed in between two transmitters. So the reason for providing this kind of configuration is to reduce the physical aperture, where you can see over here this distance SL and SW, it is reduced one we are getting, where it is of around 84. This one is 84 mm, where this is 50. This is 60 mm. So we are reducing nearly 24 mm size. Well, so this was one of another configuration of the MIMO radar, where the side lobe levels are being reduced. Okay. So now let's discuss about the actual problem visualization. So what is the problem? I was discussing that, as I was saying, the MIMO radars are being installed behind the car bumper. That means what? That means, as I was saying, the car industry are not interested to show their sensors outside, because that may hamper the outer body look of that car. If you are also looking, if you are now seeing also, whenever we purchase a car, we see that how exactly it is looking outside, that aesthetics of that car. So if we are installing some of these radars, all these things outside, definitely this aesthetics is going to disturb. So that is why now this industry are now placing these radars or the antenna behind the bumper. But what is the problem by installing it? When they are installing behind a bumper is a very lossy material. Lossy dielectric is there. Apart from that bumper material, or the front bumper or the back bumper of the car, that is also being kept with multiple layers of the paint, with a very high dielectric constant, or with glossy material having some nano metallic paints also we are using. At this millimeter wave frequency, or the 77 gigahertz frequency, this is very prominent. These effects are, though the paint layer is in micrometer range, Still, because of the millimeter high end of millimeter wave frequency at 77 gigahertz, this installation is very problem, creating very problem, and that is affecting the. As you can see from the schematic, this antenna, it was radiating. This is sensor, which is the antenna or the radar. When it is kept inside the bumper, it is providing the same good radiation, or these straight lines are considered as the good radiation. When the bumper is being installed, when the electromagnetic wave is coming outside, it is coming completely distorted. These wavy structure are being provided to show the distorted. The straight lines are providing the good electromagnetic radiation. So what is the solution? Definitely you cannot change the bumper material or bumper, because this is what a car or a automotive industry is meant for. So the reason is that you have to optimize the position in such a way that you can provide some good solution out of it. So what is the, during this process, during the electromagnetic simulation, and to provide a solution for this problem, what are the different problems we faced and how we provided the solution? Let's go towards that. Well, so what we have done initially, we have first designed one in electromagnetic simulation environment. We designed a very small kind of bumper material, that is a completely flat material we have designed. We designed one 77 gigahertz the millimeter wave antenna, and we started simulating. So when we started simulating this kind of, as you can see, this table provided, we are using gray primer, clear coat we are using with a dielectric constant of 9, with a thickness of 16.5 micrometer, with a loss tangent of 0.1. Similarly, the clear coat or properties also provided. So when we are using, because the 6 to 7 layers of paint is being used in a car, in a bumper, so we have also used the same, and we also took some information, the data of this material from this open source which is available, that we have taken, and we have started simulating. So when we have kept this structure into the simulation environment, CST, we were using CST at that time. So when we saw that after simulation, it was showing very high simulation time, means completely 1 day it was taking with a very small structure. And after being taking so much time, it was showing that memory insufficient. This is one of the screenshot I have taken. It was showing that your computer is not enough memory. So this is one of the very practical problem that probably we are facing if we are considering this millimeter wave application, electromagnetic simulation. So what we thought, that let's first solve this problem. Before we are planning to solve the actual problem, let's solve this problem first. If we are installing something and we are designing an electromagnetic environment, it is showing this kind of problem. So the solution two kind of solutions can be provided here. Once you increase your system memory. By the way, the problem what you faced, the RAM was 32 GB. So first of all, you increase your RAM, you can get the solution. Okay, this kind of problem will not come. Solution time also reduce, and the memory requirement also reduce. Or you go for the cluster computing, you can go for the workstation. That is one of the expensive way to do that. Definitely you can use that, and people are in industry you are using, because they are not simulating very small structures. They are simulating very, very big car structures, or in defense kind of things. They are using completely a ship, or they're simulating a completely one helicopter or airplane, where to see the electromagnetic effects. So how they are doing, though they are doing for very big cluster computing and workstation they are using, in our lab environment, what we can do that, so we have provided some mathematical modeling to that. So why not, our thought that why not we convert this multiple layer to a single layered approach, so that we can reduce the simulation time without affecting the accuracy of the solution. So we found two different approaches to convert the model. So the first approach was to convert it to a completely a single model, where the bumper as well as all the paint layers converted to a single, having the complete same thickness with a single material. Means, so all things are considered into one. And in approach 2, what we have considered, let the bumper be in the first stage, and only we will convert this multiple paint to a single layer of paint, where we are going to use the effective model, so that dielectric property what we will consider for this complete will be equivalent to this one. So how we have done that? We have now two approaches, and further we are having two different mathematical formulation. One is mathematical model based on the parallel plate capacitance model. Second one is the model based on the same transmission and the reflection. Out of these two models, where we got two different equivalent approach for the dielectric constant as well as the loss tangent parameter, because we are considering the dielectric constant means you have to consider both the real as well as the complex quantity. That is why we have to go for both loss tangent and the dielectric constant, or the relative dielectric constant, or the part as well. Well, right now we have two different approaches and two different mathematical model. So which is the best? Let's see. So right now we can get four combinations. Approach one can be used or can be modeled using these two mathematical model. Similarly, the approach two also can be modeled or can be converted to equivalent model using these two models. So what we have done, first we went for approach one, and the same design as I was saying. Let's take a very small flat bumper with some multiple paint with a 77 gigahertz small antenna at the silicon base we have considered, and we have done simulations. So as you can see in approach one, where the time was taking 50,348 seconds, we could able to reduce to 89% in equivalent model 1 and 87% in equivalent model 2, and this is the simulation result. The red one is the actual model, and this other equivalent model 1 and 2 are being defined by these two things. But the problem is that the accuracy was not completely 100%. So let's go for approach 2. Then we went for approach 2. Approach 2 means where bumper and paint were kept aside with the two different layers. Well, as it was, the layer was taking the same simulation time, but in this approach 2, equivalent model 1 was getting a 60% of reduced simulation time, and equivalent model 2 is getting minus 57 or the 57% of the reduced simulation time. So we found out that the approach 2 equivalent model 2 combination is providing more than 50% of simulation time, but without affecting the accuracy. We are getting completely same as we are discussing as the standard layered model. Well, let's verify with some actual antenna design. See, this is a curved bumper we have considered, because as we know, the car models are not uniform. It is being different from different manufacturer. So we have taken a curved bumper just for the one experiment purpose, where this thickness, this edge thickness is different from this middle, this part thickness. The thickness is varying from one end to other end. And here we are using the MIMO radar, where we are having the 2 transmitter and the 4 receiver configuration. And as you can see over here, the earlier we were taking 2 hours 34 minutes 2 seconds simulation time, that is reduced below 51% by taking the approach 2 and equivalent to combination model. So again, we found that yes, the mathematical model that we proposed, that is providing a 50% of simulation time reduction without affecting the accuracy. This is the simulation what we have done, equivalent model 2 and the layered model that is providing the same, that is providing the completely same result. Well, just another thing to notice is that you can see now, because this antenna is installed behind a curved bumper, now this kind of the distortion, we can see the distortion. But the point is that this is a very simplified structure, but if we install it in the actual car, that we may get more again disturbances, because earlier as I was showing, the smooth curve was there, now the smoothness is gone. We are getting very distorted radiation pattern. Okay, so another solution, let's move towards another equivalent model solution. If we are doing integration, how we can further reduce it? So another topic or what we can discuss is that how to reduce the again simulation time without affecting the accuracy is the equivalent source modeling of the antenna and bumper integration. As we know, from our Huygens principle or the surface or volume equivalence principle, we can convert one source to its equivalent source model by considering the electric and magnetic field which is being traveled around it. So this is the actual source and this is the equivalent model source, and these are the equivalent sources based on this boundary condition is being developed. And this is the well-known theory that we have used, and that is also we can use using CST Microwave Studio. So here it is the actual antenna model or the actual source, which is providing a E field pattern of this kind with a maximum of 26.1 volt per meter, it is in the dB scale. If we are converting this actual source to equivalent source, because we are converting to the equivalent source, it's a near field source model using tangential electric and magnetic field, we are getting exactly same radiation with the same value. However, this antenna simulation was taking suppose half an hour or an hour of simulation. This simulation or this equivalent source model is taking just few seconds of simulation time. And if you now install it, let's install this equivalent source with the bumper. This is a bumper model, 3D CAD model. Let's, after installing, what is the problem you see. So the blue one, this is a complete flat response or a very smooth radiation pattern we are getting, where we are now installed it behind a bumper. Now you see back lobe radiation, side radiation, multiple things are coming with the increasing dielectric constant. This was a study what we were doing. By increasing the dielectric constant of the bumper, we are getting a very different or a very distorted radiation pattern. This was the what I'm discussing about how is the problem. Well, again, let's discuss about in the 2D plane. If antenna is being installed without installing this radiation pattern, with installation, if you're talking about different cases at the transmitter antenna as well as the receiver antenna, we can see the pattern is being distorted in this case. Either we are getting higher side lobes, where we are getting some distorted main beam, where this kind of problem we are getting. Well, so we know that this kind of problem, suppose we are providing a solution to this kind of problem. So how exactly we can quantify it? So there was no such parameter was there to quantify it, though we can provide some logical solution that, okay, if we are getting some smooth pattern, we can say that our solution is very good. So let's define few parameters. Means when we are designing one antenna, we are seeing that, okay, let's see if the antenna is below minus 10 dB, this antenna is working properly. So if we are providing this kind of, we are facing this kind of problem, what kind of parameter we can define? So we have to define some parameters. So logically what we have done is that we have defined two parameters. The first one is the bidirectional loss model. That means if a sensor is being installed behind a bumper, based on the radar concept, it will transmit the electromagnetic wave, it will hit the target and it will come back again. So the bumper is providing twice the loss while the transmitting and receiving both the complete path of transmission and reception. So how we can model the loss? So first we can model the dielectric loss that is being done by the bumper model, by the bumper itself with the paint layer. Again, the mismatch loss because of the reflection from this when electromagnetic wave is traveling from this air medium to the dielectric medium. Again, when it is traveling from the dielectric to the air, it is being done by twice. So the total loss is equal to twice the dielectric loss and the mismatch loss. So this is the first parameter. Well, so but this parameter is independent of the curvature effect of our bumper. So whatever the electromagnetic we study in our textbook, we discuss only about the flat surface. We never discuss about the curved surface. So how to incorporate the curved surface? So what we have done. So this is the loss parameter that we computed using the mathematical formulation only. But this output can only define for any kind of bumper, flat bumper. We cannot define if we are changing the bumper, if you are changing the models, how to incorporate that curvature effect. So to incorporate the curvature effect, what we have considered, the pattern distortion being done by a certain bumper will be considered as the change in the bumper. So logical what we have considered, if we change the bumper, we will get the change in the distortion level also. So that distortion parameter we have incorporated in this mathematical model, and we found out that this is the curve that is providing the bidirectional loss model in the field of view of minus 100 to plus 100, or you can take minus 80 to plus 80, complete 160-degree field of view. Within that we can calculate which is providing a loss of below minus 10, below 10 dB or 10 dB or 15 dB. This is the dB scale. Well, how to identify whether it is correct or not? So what we have done, we have developed our parameter and we have sent to Mercedes Bench. They had their internal algorithm. They compared with the internal algorithm. They found that both the response are completely very close to each other. The black one is the model that we provided. The blue one is the model that is the internal algorithm of the Mercedes-Benz that is matching very closely to each other. So we have considered that is one parameter, and also we started studying this parameter. If we reduce the losses with our solution, if the losses are being reduced, then we can say that this is a good model, a good solution we are providing, even if the antenna is being installed. Okay, this is the first parameter. What is the next parameter is? The next parameter is the antenna array ambiguity function that we proposed. So the ambiguity function it is not the ambiguity function that we discuss in the radar perspective, but it is the antenna perspective of the ambiguity function that is being developed using the pattern. So let's discuss that one bumper model that was I discussed earlier, the curved one, how the bidirectional loss is varying. Then I will come to the antenna array ambiguity function. Well, so this is the zoomed in part. So here you can see as the dielectric constant is changing, the bidirectional loss is changing, but it is not changing very uniformly because the bumper is not a flat bumper. If it is a flat bumper, as per our textbook study, we can see the increase in the loss as the increase in the dielectric property. Because the curvature effects are incorporated, because of this change in the curvature, the reflection angle is also changing at the different position. That is why the loss is also changing at different positions. This is the first parameter. Next is this is the antenna array ambiguity function. These are the curves, or these are the diagrams or the graphs that is providing the information about the ambiguity function. So what is the information we are getting? I will also discuss very clearly how to interpret this curve. So just to show you that, you see that when the bumper it was not installed, the curve was very smooth. The red part or the angular part, this angle is very smooth, where we are installing a bumper in this case with the figure number H, where the different paint layers are there and different also dielectric constant increased. So you can see now it is very showing very distorted things. Means that the middle part, what exactly the red one, it is now gone, and the additional things are being come up. That is shows the about our false alarming. So how to interpret this, I will discuss it. Well, let's see. This is the equations that we are using to find out the antenna array ambiguity function. This is the transmitter function, or the shading vector, receiver shading vector, and this y of alpha is nothing but your chronicle product between the transmitter and receiver. The antenna array ambiguity function defines your modulus of y of h, the Hermitian matrix, multiplied by the matrix itself divided by this is the norm operator of our y of alpha I and the j, where I and j transmit from 0 to 2 pi. So this is what for a two-dimensional or the 2 cross 1D MIMO. As I was talking about, 1D means it is the only azimuth not considering the elevation as discussed earlier. So this is what this line is called the field of view, and this thickness is called the resolution. If the resolution is improved, then this thickness will reduce, and if the field of view will distorted, then means if you want to check whether our design providing high resolution, then this part will completely reduce. That means resolution is high. If this is increasing, we can say that field of view is increasing. If it is being distorted after installation, that information will get that how this information is being distorted. Well, now see how it is being installed and seen. This is the only standard antenna, two-dimensional antenna with a bumper is being installed, and these two parameters studied. The one bidirectional loss also studied, and the bumper the ambiguity function also studied with different dielectric, where you are seeing that at the dielectric, at the coat, paint layer, primer, base coat, when we are installing, the field of view you see compared to this field of view, this field of view is reduced. Means our actual field of view is being reduced after installation. Means installation has an effect on the field of view also, it is reducing. Also, it is increasing the losses in the field of view. These are the two parameters that you can define completely quantitatively what is happening after installation. Without only seeing the radiation pattern, we can quantify it by using these two parameters. Okay, let's move towards the 3D let's move towards the 2D MIMO radar. So what is the 2D MIMO radar? Means the MIMO radar now will work in the elevation plane also. So these are the antenna configuration where one antenna is being shifted towards the Z direction. So that is also designed at 77 GHz operating frequency, And this diagram is providing that how this physical array is converted to the virtual array, both in the azimuth and the elevation. So earlier, as I was talking, the virtual array only in one dimension, that is x. Now the virtual array is being designed for x as well as the z direction. Means this is the elevation, this is the azimuth direction x, and z is your elevation direction. That is also virtual array we are getting. Based on this 3x4 antenna configuration, by shifting a position of our antenna, we can get. Similarly, right now people are now getting thousands of virtual array to completely getting a 4D system of the 4D system to properly identify, and the imaging purpose also people are using for the automotive radar. Inside also using in car to identify the positions of the sitting position of our driver as well as the passenger. Similarly, we are keeping also outside to identify the pedestrian and the other obstacles. Well, so now we are integrating the antenna with this same antenna with the bumper. The same integration process is being carried out again to observe how exactly it is being affecting the mutual coupling. As I was talking, the MIMO mutual coupling is a prominent thing to identify. So we see that after installation, mutual coupling also is also increasing due to the multiple reflection between the transmission between this radar and the bumper material. Well, so these are the performance study. Again, if you see the 2D and 3D MIMO radar concept, just to see, as I was discussing, as this thickness is being reduced in this case, means 3D MIMO radar or the 2D MIMO radar is providing better angular resolution compared to your 1D MIMO radar. This is just a comparison to show. There is no installation over here. Okay. See the improved field of view and the improved resolution. When we are changing from 1D MIMO to 2D MIMO, at the same time, if you are changing number of antennas over here increased. As I was saying, if you increase the number of transmitter, here you are getting 3 into 4 is called the 12 virtual array. Here we are getting 2 into 4 is called the 8 virtual array. Because the virtual array size is increased, the resolution is also improved over here. Well, so now if we install our antenna, there are different cases. We just for our sake of understanding, we will see that the first one and the last one, you see this is the antenna or the field of view antenna or ambiguity function study, where without bumper we are getting a good field of view and good resolution. Similarly, if you say the final one, you say that our field of view also reduced, as well as our angular resolution is also affected. We are getting some additional clutter also over here due to the side lobes. So this is what the problem. So how to get the solution out of it? Let's see the proposed solution that we have provided to the Mercedes-Benz. So what we have done is that we have used a binomial n section matching layer concept that was already available in our microstrip line theory, where we have commensurate sections, means equal sections transmission lines are there with a load of ZL and with a characteristics impedance of Z0, which is being very starting part, and other part are the matching section. If we are calculating mathematically, then we can get the matching layer dimension and the property of Z, the characteristics impedance of this matching layer by this equation of ln Zn plus 1 by Zn is equal to 2 to the power minus n. See the combination n and ln ZL by Z0. ZL is our load, Z0 is the characteristic impedance of the air or the normal transmission line or 50 ohm transmission line we can consider. In this load as well as the 50 ohm transmission line, if you try to do the matching section, you'll get this kind of equation we need. So we have converted our problem statement to this kind of matching section designing. However, we are not using transmission line concept. We are using the material property concept by changing the characteristics impedance to the field or the wave impedance. Well, so this is what Z0 part we have kept the sensor, and this bumper part we have considered. Again, as we have discussed, we have converted the bumper to a layered model, and this layered model is being considered as a load, because this is the load. We want to match the load with the electromagnetic wave that is coming from sensor, and in between this we are going to use our matching section. So these are the effective medium theory we have used to convert layered to a single medium. Again, this is the equation we are using. We have converted like this. Further, this is the matching layer section or the binomial n section matching layer we are going to use in between the sensor and the bumper, so that we will get the reduced reflection at the highest matching to that will provide the reduced bidirectional loss. So what we have converted the transmission line model to the wave impedance model, so where we can directly get the dielectric property of the matching layer. So with this concept, we provided actually a two-layered matching layer section. This is the matching layer 1 mathematical model for the matching layer 1, and this is the dielectric property of the matching layer 2. So this is now we can use like this. Means the paint is there, the bumper is there. We can use two matching layers. We can use n number of matching layer. We can use only one matching layer. We can use two matching layer based on our requirement and what we are going for it. So based on our requirement and feasibility, we can introduce either a single matching layer or BML or the binomial matching layer or the two layer of section we can use. So based on this approach of solution, we got a joint patent with IIT Bombay as well as the Mercedes-Benz, and this patent is also being granted. Well, so what is the next? What is the solution? Also involves automation. So what is the automation is there? Means if we are designing a matching layer to reduce the losses for a bumper, means there are n number of car models are there. So we cannot go for each car and we have to find a solution for each car. So we have to automate it. You provide a bumper, the output of the automation will be providing a matching layer that is compatible to that particular car only. So that also we have provided a mathematical tool also provided. That tool will consider the sensor spacing or the specs of the sensor, means what is the frequency, what is the field of view, what is the material, what is the number of paint layer you are using. That we will give to this mathematical model or the mathematical tool, and the output when we will click OK, then we will get the layered, the completely matching layer you will get that is going completely matched to this particular car. Well, so how exactly the mathematical tool looks like. So this is the tool development flow chart. So we have to consider a STL model, then we have to go for because in the electromagnetic simulation tool we can get the mesh cells generation. From this mesh cells we can get the actual position or the curvature effect also we can consider. From this curvature effect, this is the triangles, means different points that we are getting in these meshes we can get. So from this point we can find the actual thickness of because the bumper thickness can vary from position to position, so that we can get the actual thickness and we can provide the solution based on the approach of the binomial matching layer we are providing. So this is the one schematic that if the thickness is varying in different places, we will get the varied thickness of our matching layer with different dielectric constant at different positions. And that is also part of this granted patent. So how exactly the tool looks like? This is the tool, and this is our software model also there that is being developed using Python, where we are using some input of the frequency. We have to give which frequency, millimeter wave frequency in gigahertz, which model, CAD model, which car. This is a car, you take a model of the car, then you give the dielectric constant, loss tangent, paint material, everything you give, and you choose the model like one layer, two layer, the binomial matching layer you are using, then put OK, submit it, then you will get the layered section of output. So then what we have done, we have implemented also that, and we found we have used our model for three different validation. We have used for three different bumper designs. So these bumper designs I have not shown because of the confidentiality from the Mercedes-Benz. Only I am showing the solution or the result out of it. So the bumper model 1, 2, and 3. First, let's see. So the green one, the green color one is the two-layer bumper model solution. The blue one, when there is no matching layer, only the bumper was there. So by using the matching layer, the solution, you can see the loss is being reduced completely from 4 dB to 2 dB. It is reduced. The 50% loss is being reduced in one design. Now next we have used in the second model. In the second model, there was very high loss at the end of our field of view. So by using this solution, we are able to reduce the loss from 12 dB to 6 dB at the both side of our field of view. Similarly, in the third bumper model or the third car model, we have used the solution. Again, we found a satisfactory reduction on the losses within the field of view. So we found that binomial layer is providing overall reduction of bidirectional loss over the field of view. The loss is being reduced. That means, so our proposed solution and the automation model is working properly in the actual environment and condition. Well, as we are not saying that this is the completely or this is the final solution. Definitely not. We can definitely improve this solution in a better level itself to get a completely zero. Whether the ideally should we are looking for zeros or loss, so that may not possible ideally zero, but we can definitely can improve our solution to the greater extent. So how we can implement it in actual model? In the car model, the advantage of proposed method over others is that industrial paint rovers are now dedicatedly, we can use dedicatedly to use our matching layer at the behind the bumper. We can throw our paint. We can that also automation can be done where with actual thickness and the dielectric property can be used to get the solution or to put the paint layer behind the bumper. So this is the way, starting from a problem of the millimeter wave radar design to the complete solution we have provided to the industry. Well, so at the conclusion, what I would like to say is we have discussed a brief about the ADAS or the Advanced Driver Assistance System and the sensor technology that is being used in the autonomous vehicles. Then we have discussed about the 1D and 2D MIMO radar working principle and the antenna. Then also we have studied the performance evaluation of the integrated antenna MIMO radar structure behind the bumper. Then there was a discussion of simulation time reduction with effective efficiency, as well as we also discussed about the solution of the mitigate the integration losses. So this was from my end, and I would like to just refer that based on this idea, we have also published one book chapter on the Springer, the Handbook of Metrology and Application. The title of the book chapter is Antennas for Millimeter Wave MIMO Radar, Design and Integration Challenges for Automotive Application, that people can study if they are interested. Further, based on my other research work on full duplex, also we have got another book chapter on RF, microwave and millimeter wave technology, where the title is about the antenna for full duplex communication, state of the art and way forward. That these are the two different. The first one is for I was discussing the same, and this is the full duplex communication for as well as the antenna domain topic is concerned that we have highlighted here. So thank you so much from my end, and thank you so much for listening carefully at this time. So I would like to hand over to sir now if you have any question or I would like to take a few.
What is the duration of this project, sir?
So it was nearly 3 years. We were working continuously with Mercedes-Benz to get a problem statement to solution. Apart from that, also I was continuously working during my apart from the industry. Also, I was working on my separate research project. I was taking. I was working at ISC at the same time. Right, now, my students are working it in IIT Rourkela also.
What is the team strength, sir?
Sorry.
How many members worked for this project, sir?
Okay, so frankly speaking, from academia side, I was working, and one with me, one BTech student was helping me to develop this Python model. So two from my side. So I was the actually doing complete work from this project. I was completely doing it, and the BTech student was helping me. And from Mercedes-Benz side. Prof. Dr. Doot was there, and with two other members, they were assisting that how to look at the problem, or you can think in a different way. So they were assisting from their end. So, but I was implementing from my end with the BTech student help.
Nice session, sir. Even though we didn't find so many workshops we are attending, this type of complete description and point-to-point explanation is we didn't find anywhere, sir. And AR finding, is there any particular procedure for AR, sir?
Sorry, can you please repeat?
For MIMO radar, sir, AR finding, axial ratio.
Axial ratio. Okay, fine. Very good question, by the way. So the axial ratio, all these antennas. Okay, should I stop presenting? This, I think repetitivity is okay. Let me stop it presenting. If you want, I'll show you. So for this MIMO radar, the axial ratio, what we are considering, this is the linear array, and these are the axial ratio. This is not a circularly polarized. These are the linearly polarized antenna we are using. So the axial ratio is not very good to discuss over here, because only for the circular polarized antenna we are considering the axial ratio below 3 dB, but because it is a linearly polarized antenna, so axial ratio is we not considering over here. And because of the design challenges, only the linearly polarized antennas are very useful over here, I would say, because for the circularly polarized, we will get some left hand circular polarized and right hand circular, two different things. So reflection after getting, if the polarization changes, then we cannot get the actual information. So here I would say the linearly polarized one is the better one. Yes. So I hope my answer is okay to you. If you want anything, I would definitely would love to answer.
I hope the question is answered. Sir, there is one question in the chat box by Maruti Prema. What is the purpose of matching layer in bumper?
Okay, so that was what the complete solution was looking for. Uh, the point is that we cannot, as far as the industry standard or as far as the industry norms, I would say the requirement, we cannot change the position, because as the automotive industry, they are procuring radars or the sensors from a different industry. Suppose Bosch, Continental, these are some industry from where they are taking the radars. Because if you're talking the Mercedes, they are not radar company, they are the automotive company. So they leave space, only some space, to the electromagnetic engineer to install the radar. So we have to optimize the position within that limited space, and we have to find the solution within that space. So that matching layer what we provide, that is not the behind the bumper, that is completely not altering the vehicle design. At the same time, it is reducing the reflection that is coming from the radar and the bumper integration, and at the same time it is also improving the field of view that was being distorted by the integration of the bumper. So that is why we have provided this solution of the matching layer to reduce the reflection losses and the mismatch losses that was being done by the bumper, to get a better field of view and to reduce the losses. That is why we have provided this solution, considering the different modalities that was being provided by the industry.
Okay. There is one more question from the same participant.
Okay.
Does LiDAR needs point of sight with respective recipient in order to do its function?
Can you just repeat the question once again? That LiDAR needs?
Yeah, the question says, does LiDAR needs point of sight with respect to recipient in order to do its function?
Okay, okay. Again, it's a very good question. So definitely, because it is also depending on the beam what lidar is sending, because it is a point beam, as you have identified. It is a point beam. We are not transmitting a only single beam. We have to transmit the multiple beams or the multiple rays from the lidar to get it identified properly. Because the only antenna that is providing a complete beam pattern, we can identify an object properly. But for the lidar, we have to transmit multiple point beams to identify the other object, and that is how the lidar is being more providing better resolution compared to the radar, because of this point beam transmission compared to the, or very pointed beam transmission compared to the radar. However, definitely, as I told, it is not effective in case of our harsh weather conditions like the rain, fog, and all, where the now people are now improving the radar from 3D radar to 4D radar to get the elevation information also. But yes, as far as the lidar is concerned, we have to transmit multiple point beams to identify an object. Yes.
Yeah, participants, if you have any more questions, you can unmute and ask, or else you can type your query in the chat box also.
Sir, what is the future technology for all the electrical vehicles with respect to your research?
Well, based on my limited knowledge, I would like to share with that as far as the electric vehicles are concerned, that are mostly the research are mostly the BMS, is the battery management system, and they are working because of, as you can see right now, The as far as my research is concerned, definitely that part is there, because these are very low power systems. That is there because you want to also provide the active safety during the travel. So only the difference, I could say, the fuel is changed. Right now the battery are being used in electric vehicles compared to the earlier. The petrol or diesel or liquid fuels or any gas fuels are being used. So the research are mostly based on this. If radar is there, everything will be there. How to reduce the power consumption to effectively increase the travel time of a autonomous vehicle or any electric vehicle. So the most of the work is going on the battery management system, how we can provide a better battery life, high charging speed with better increasing the, and or the right now more specifically I would say the wireless charging system, also wireless power transfer also it is being used. It is the RF based research. So suppose we cannot use all the time a plug system, so how we can efficiently wirelessly, so we have to prepare a platform where the car will, like we are doing our car wash, we are putting in a platform and we are washing our cars, like similarly we provide a main platform where the car will charge within wirelessly within a few hour, within an hour that can charge a complete. So battery power supply system and this wireless part, as well as our semiconductor technology for this to improve this PV, the photovoltaic cells. If you're installing in a car, if it is travel time also, it can continuously being charged, will provide it. So the electric vehicle as far as EV is concerned, these are the research are more prominent, including the research of wireless power transfer and the antennas. All these things are being there. We are not replacing anything. We're trying to just reduce the power level.
Thank you, sir.
Thank you. So, anything else if anybody would like to ask?
Yes, participants. Yeah, there is one more question, sir. Do we need more than one radar to be integrated in a car for getting 360-degree object detection?
True, it's a very good question, by the way. So yes, we need multiple radar, MIMO radars, by the way. So as I was discussing, then this is the front profile. If you want to check, we are going for front bumper. Then rear bumper also we need another to check the back side of our vehicle, which is what is coming or not. At the same time, ORVMs, the vehicle ORVMs, the mirrors also, there are these places where we are using the radars to find out to blind spots, detect the blind spots. So yes, multiple radars are required, and that is how as I discussed, the sensor fusion technologies are being used to place multiple radar in the multiple section without affecting each radar to each other, so that we can fuse the data information what we are getting from all the radars, and we can provide a more robust model to provide a solution whether how to act for an autonomous vehicle. Yes, multiple radars are required.
Yes, any more questions, participants?
Okay, if not, then means you can definitely I have provided my email ID and contact also. If you have anything, you can write an email or something. We can work or in anything we can do also. We can respond in emails or something like that also if you want. Yeah, over to Gaurav sir.
Yeah. Ranjan madam?
Yes, sir. Now we can conclude the session.
Yeah. Is there any photograph to be clicked?
Yes, photograph is
Yes,
to be
yes,
taken.
will take.
Yes.
I request all the participants to please turn on their cameras for a minute.
All are ready? Yes.
Yes, madam.
Yes, ready.
Done.
Thank you so
Thank you.
much.
Yeah, so thank you, Dr. Jogesh sir, for that insightful presentation and engaging and interactive session. I'm very much sure that we all have better understanding of MIMO radar antenna design, integration effects, and its solution for autonomous vehicle applications. Thank you, sir, on behalf of Department of Electronics and Telecommunication Engineering of VESIT and all the participants.
Thank you so much, Saurabh sir and Dr. Bala for providing this opportunity to share my thoughts. Thank you so much. Thank you so much again.
Thank you, sir. Thank you for joining us.
Thank you. Good night, all.
Good night, sir.
Yeah, thank you all the participants for their active participation. We will meet with another insightful and knowledgeable session tomorrow. Thank you.
All the participants are requested to fill the feedback form. Yes, you will get the session recording in the form of YouTube link. Please wait. Mostly you will get it tomorrow.
Please note that feedback link will be posted in the chat box only. So complete your feedback and then only leave the meet.
Also, please enter your full Atal ID, VS Atal, your number, which is given and shared in the WhatsApp group.
Chintan, once again, please post the link. One participant has requested.
Monali ma'am.
हाँ चिंतन
मैम एक पार्टिसिपेंट का है ना आईडी नहीं मिला है बोल रहे हैं। एक सेकेंड ना, सुचिता मोहन पवार, वो आईडी बोल रहे पूछ रहे उनका। वो लिस्टेड नहीं है।
हाँ 147 बोलो उनको डालने के लिए 147
ना?
हाँ यस
ओके मैम, ठीक है, थैंक यू।
Okay, ma'am. Thanks, ma'am.
यस
147.
7.
Thanks.
I think now we can close the link.
Yes, madam.
Chintan?
Okay, ma'am.
All have filled the feedback form. I think sufficient feedback forms.
Just a second, ma'am. हाँ मैम 100 क्रॉस हो गया।
Now, Manisha ma'am, Manisha,
is asking both the
please
feedback form again.
stop the recording. Manisha, you please stop the recording.
Ranjan ma'am.
Yes.
Somebody is asking both the session feedback form link.